Tonight we are going to travel backward through time, past the continents, past the oceans, past the first living cells to an age when Earth itself was still unfinished. The world was hotter then, younger, a place of molten rock and drifting planetary debris circling a newborn sun. And somewhere in that ancient darkness, another world was moving beside us. Scientists call it Theia, a lost planet roughly the size of Mars that may have shared Earth's orbit for millions of years before everything changed. What followed was the largest collision in Earth's history, an impact so powerful that it vaporized worlds, created the moon, altered the length of Earth's days, tilted the planet's axis, and perhaps helped make life itself possible. This is the story of the planet that disappeared so that our world could become what it is. Before we begin, please consider liking this video and subscribing to the channel. It helps others who enjoy these calm science explorations find their way here too. Now settle in and let the noise of the day drift farther away. The story you are about to hear began 4.5 billion years ago in the deep silence of the early solar system, long before there were mountains, oceans, or eyes to look up at the moon and wonder where it came from. Long before the moon hung in the sky, long before the oceans filled their basins, long before the first breath of wind moved across any surface anywhere on this world, there was only a cloud, an enormous, slowly rotating cloud of gas and dust, drifting through a quiet region of the Milky Way galaxy, holding within its cold and patient darkness all the ingredients for everything that would ever exist in this corner of the universe. The solar system formed approximately 4.6 billion years ago from exactly this kind of cloud, what scientists call a solar nebula. As gravity began to draw the cloud inward, the material at its center compressed and heated until the pressure became so great that nuclear fusion ignited and our sun was born. The rest of the cloud, everything that did not fall into the star, remained behind, flattened into a vast spinning disk of leftover material orbiting the newborn sun. Dust settled. Grains of rock collided and stuck together. Pebbles became boulders, boulders became mountains of slow-drifting rock, and mountains became the earliest seeds of worlds. That disk of swirling debris was not the calm and ordered solar system we know today. It was violent and crowded and magnificent, a churning sea of material in which collisions happened constantly, in which bodies grew and shattered and grew again, in which the future was being decided grain by grain, impact by impact, across millions upon millions of years. And somewhere in that disk, circling a young and restless sun, the first chapter of a story that would eventually lead to you was already being written. The solar system we know today, with its 8 orderly planets, its asteroid belt, its distant rings of icy debris, took a very long time to settle into its present shape. In the earliest period of solar system history, the environment was almost unrecognizable. Within the first 10 to 20 million years after the sun ignited, dozens of planet-sized bodies called planetary embryos had already formed throughout the disk of swirling material that surrounded the newborn star. These were not small objects. They were true worlds in the making. Bodies large enough to have their own gravitational fields, large enough to pull in surrounding debris and grow steadily larger, large enough to develop interiors that separated into distinct layers of different densities. They formed through a process both violent and patient, in which smaller bodies called planetesimals, themselves already the result of millions of years of gradual accumulation, collided and merged until something truly substantial emerged from the chaos. The inner solar system, the region close enough to the sun that rock and metal could remain solid, was especially crowded with these growing bodies. They jostled against one another in overlapping orbits, their gravitational fields tugging at each other across the emptiness, nudging and destabilizing and drawing ever closer to the inevitable encounters that would eventually sort the solar system into the arrangement we recognize today. Most of these embryos no longer exist as independent worlds. They were absorbed, they merged, they were flung outward into the dark. But for tens of millions of years, they populated the young solar system like a generation of worlds that never quite got to survive. Among all the worlds that formed and vanished in the turbulent youth of the solar system, there is one whose story we tell with particular reverence, because its story is also ours. Theia is the name given to one of those early planetary embryos, a body that scientists believe grew to roughly the size of Mars before its fate brought it into catastrophic contact with the young Earth. We have never seen Theia directly. There is no photograph of it, no ancient record carved in any stone, no fragment of its surface that has ever been touched by human hands and identified as belonging to it alone. It existed and was destroyed before any living thing existed anywhere on this planet to observe it. What we know of Theia has been assembled painstakingly from the physics of planetary formation, from computer simulations run on modern supercomputers, from the chemical signatures buried deep within moon rocks returned by astronauts, and from the slow, careful logic of what the solar system must have looked like in its earliest chapter. Theia is, in every meaningful sense, a world reconstructed from clues, a planet whose existence is inferred rather than directly observed, whose shape and size and journey can only be estimated, whose final moments can only be modelled. And yet the evidence for Theia's existence is strong enough that it has become the centerpiece of the dominant scientific theory for how the moon was born. A world that no longer exists, whose ending was so total and so violent that nothing of it survived intact, and yet whose legacy touches every tide that rises on every coast of every ocean on this planet, and every night that the moon sends its quiet light through a window onto a sleeping face. To understand the scale of what Theia was, it helps to begin with Mars, because Mars is roughly what Theia is thought to have resembled in size. Mars is approximately half the diameter of Earth. It is a world large enough to have a thin atmosphere, a varied and ancient surface, towering volcanoes and vast canyon systems stretching thousands of kilometers across its rust-colored plains, polar ice caps gleaming in the weak light of a distant sun, and the preserved evidence of ancient rivers that once ran across its surface before the water was lost. Mars is, by any measure, a substantial world, and Theia is believed to have been comparable to it, not a fragment, not a pebble lost in the enormity of space, but a true planetary body with its own gravitational field strong enough to pull in surrounding material and hold it. That gravitational field would have shaped Theia's interior just as Earth's gravity shapes ours. Material would have settled according to density, the heaviest elements, iron and nickel, sinking toward the center under their own weight while lighter rocky silicates rose toward the surface, forming a layered structure not so different from the layered structure of Earth itself. Theia had mass. Theia had weight. Theia had geological complexity. It was a world in the fullest sense of that word. Not finished, perhaps, not ancient and settled the way Earth is today, but a world nonetheless. A world with its own history that spanned tens of millions of years before it ended. A world that, had the gravitational architecture of the early solar system arranged itself only slightly differently, might have survived to this day, orbiting the Sun as a second rocky neighbor to Earth. The solar system is vast, almost beyond imagination. A gulf of space in which the distances between worlds are so enormous that even traveling at the speed of light would require years to cross from one edge to the other. And yet, in the context of that immensity, Theia and the early Earth were neighbors in the most intimate astronomical sense possible. Theia is hypothesized to have formed in the same orbital region as the early Earth, in the inner solar system, within the zone where rocky planets take shape, where the sun's heat is strong enough to prevent volatile ices from condensing, leaving behind only the denser, rockier materials that become terrestrial worlds. This proximity was not a coincidence. The same region of the proto-planetary disk that gave rise to the Earth was also fertile ground for other growing embryos, and Theia was one of the products of that same fertile zone. It drew from the same reservoir of raw materials, the same silicates, the same metals, the same chemical inventory that the disk had accumulated in that part of the solar system. This shared origin would leave a chemical signature that scientists would later discover when comparing Earth and moon rocks, a similarity so striking that it became one of the most important clues in reconstructing what happened between these two worlds. For millions of years, Theia and Earth both existed in the same broad neighborhood, orbiting the same young sun, separated by space but connected by gravity and by shared chemistry. Two worlds made of the same ancient dust, moving toward each other across the slow and silent curve of deep time. Science has a long tradition of reaching into the deep past of human culture to name the things it discovers in the cosmos. finding in ancient mythology a language already built for speaking about forces larger than ordinary life. Theia is no exception. The name comes from Greek mythology, where Theia was a titaness, one of the elder gods who existed before the Olympians, vast and primordial beings who embodied the most fundamental forces of the world. Theia the Titaness was the goddess of shining light, of the gleam that emanates from precious things, of the brightness that gives gold its particular luster and gems their inner fire. And she was the mother of Selene, the goddess of the moon. The scientists who named the lost planet Theia made a deliberate and quietly beautiful choice. The mythological Theia gave birth to the moon goddess. The planetary Theia, in the violence of collision, gave its very substance to the moon itself, poured its rocky outer layers into orbit around the surviving Earth, contributed its mass to the body that has watched over this world ever since. There is something tender about this naming, a recognition that the story of Theia is as old as the human impulse to give the moon a mother, to feel in the tides and the moonlight the presence of something ancestral and generous. The ancient Greeks did not know what had really happened. They had no mathematics, no spectrographs, no supercomputer simulations. But they felt in the moon's light something that deserved to be traced back to something else, something larger, something lost. In that intuition, they were not wrong. It is difficult, from the quiet distance of the present, to truly feel what the early solar system was like, to grasp the scale of its violence and the relentlessness of its chaos. The early solar system was not the orderly, spacious arrangement we observe today, with planets moving in well-separated elliptical paths around a stable, middle-aged star. It was a violent and crowded place, dense with competing bodies, alive with collision and disruption on a scale that has not been seen in the inner solar system for billions of years. Dozens of proto-planets occupied the inner solar system simultaneously, each pulling on the others with its gravitational field, each influencing the orbits of everything around it in ways that compounded and cascaded into ever greater instability. Collisions were not rare events. They were simply the mechanism by which the solar system was sorting itself out, the way that dozens of competing embryos became, over hundreds of millions of years, the smaller number of larger planets that now exist. The bodies that grew largest grew not just by accumulating loose debris, but by swallowing their neighbors whole. Earth itself is believed to have grown through numerous collisions with other embryos before Theia arrived, absorbing them, incorporating their mass, growing hotter and larger and more gravitationally dominant with each merger. In this context, what happened with Theia was not anomalous. It was the final, most dramatic chapter in a long history of planetary violence, the last and largest collision in Earth's formative period, the one that left the most permanent and visible mark in all of Earth's history. The moon in the sky tonight is the scar of that ancient crowding and the tide mark of a solar system still finding its order. There is something almost meditative about the way worlds are made, a process so slow and so gradual that each individual step seems unremarkable, and yet the cumulative result is a planet. Theia is thought to have formed through a process called accretion, the same fundamental process by which all rocky planets come into being, a process as patient and as inevitable as the way water carves a canyon, one drop at a time across 1,000 years. In the dense disk of gas and dust that surrounded the young sun, individual grains of rock and metal drifted through the emptiness. When two grains collided at low enough velocities, they sometimes stuck, bound by van der Waals forces, by the slight electrostatic attraction of their surfaces, by simple chance contact maintained long enough to allow something more permanent to begin. Clumps became pebbles, pebbles became boulders, boulders accumulated into bodies large enough to exert their own gravitational pull, and at that point, the process accelerated. Gravity is not subtle once it gains a foothold. A body massive enough to gravitationally attract surrounding debris will accumulate faster and faster as its mass grows, sweeping up material from an ever-widening swath of its orbit. Theia grew this way, slowly at first, dust grain by dust grain, then faster as its gravity strengthened, drawing in planetesimals, swallowing smaller embryos, steadily becoming the Mars-sized world that would eventually find its orbit entwined with Earth's. Every atom of Theia was once loose in the disk, and now most of those atoms are part of the moon. or buried deep in Earth's interior, or resting quietly in the ancient rock beneath your feet. The story of Theia is, among other things, a story about survival, or rather, about the overwhelming rarity of it. Planetary embryos like Theia were not unusual in the early solar system. They were, in fact, the expected product of the accretion process playing out in a disk of material dense enough to generate them. For a period of tens of millions of years, the inner solar system was populated by dozens of these bodies, growing, interacting, nudging one another gravitationally, competing for the same raw material and the same orbital real estate in a contest that could only ever have a limited number of survivors. Most of those embryos did not survive as independent planets. The mathematics of orbital mechanics in such a crowded environment almost guaranteed eventual collision or ejection. Some embryos were absorbed into what would become Earth, adding their mass to the growing body of our world. Some were absorbed into Venus, or into the body that would become Mars. Some were flung outward by close gravitational encounters with larger bodies, thrown into distant eccentric orbits from which they never returned. Scattered into the cold outer solar system or beyond, into the silence of interstellar space. The process was not gentle and it was not selective. It was governed by the cold logic of orbital resonances and gravitational perturbations, a kind of celestial natural selection in which surviving as an independent planet required not just the right size but the right orbit, the right timing, and a remarkable degree of gravitational fortune. Theia had most of those things. For millions of years, it navigated the chaos successfully, until, finally, it did not. Inside Theia, beneath whatever surface it may have presented to the early solar system, the same physics that governs the interiors of all rocky planets was quietly and patiently at work. Theia may have had a differentiated interior, meaning that its materials had separated out according to density, just as they did inside the young Earth. Differentiation is the process by which a planet, once it has gathered enough mass to generate significant internal heat, begins to sort itself from within. Heavy elements, primarily iron and nickel, sink toward the center under their own gravitational weight, forming a dense metallic core at the heart of the world. Lighter silicate materials rise toward the surface, forming a rocky mantle and eventually a crust. This process requires heat, and the early solar system provided heat in abundance, from the decay of short-lived radioactive isotopes embedded in the newly formed rock, from the kinetic energy of ongoing accretion impacts, from the compression of material under its own growing gravity. Theia, being Mars-sized and formed within the first tens of millions of years of the solar system's life, would have had access to all of these heat sources. The implication is significant. Theia did not arrive at its collision with Earth as an undifferentiated lump of rock. It arrived as a fully structured world, one with a core, probably rich in iron and nickel, and a mantle of rocky silicate material surrounding that core. That interior architecture was what determined where each piece of Theia ended up when the collision came. The core sank into Earth. The mantle became the moon. The inner design of one lost world determined the shape of everything that followed. Around the young world of Theia, in the earliest chapter of its existence, there may have lingered something like an envelope of gas, though nothing as settled or as breathable as the atmosphere surrounding Earth today. In the early solar system, before the sun's radiation intensified and the solar wind swept outward through the disk, planetary embryos forming in regions still dense with solar nebula gas could accumulate what scientists call a primordial envelope, a thin, clinging layer of hydrogen and helium drawn in from the surrounding disk by the embryo's growing gravitational pull. This was not an atmosphere in any sense we would ordinarily picture. It was not layered or stable, not rich in the nitrogen and oxygen that sustain life, not capable of producing weather or sheltering chemistry. It was a fugitive thing, a first gentle grasping at the gas-rich environment of the young nebula, an envelope that would have been fragile from the very moment it formed. As the sun ignited fully and its radiation intensified, as the solar wind began sweeping powerfully outward through the disk, the lightest gases, hydrogen and helium, would have been stripped relatively quickly from inner solar system bodies like Theia, leaving behind only the heavier materials beneath. Theia's primordial envelope of gas was likely a brief feature of its earliest youth, a soft first breath drawn in from the nebula and then released, leaving the world more bare and more rocky beneath the growing brilliance of the young sun. It rose and was carried away by the solar wind, and the solid world beneath it continued on, building itself grain by patient grain. It is worth pausing, before we move forward into the story of what happened between Theia and the Earth, to hold in mind the picture of what the early Earth actually was during this period, because it was not the world we would recognize today. There were no continents rising above calm seas. There were no oceans to fill any basins. There was no blue sky arching overhead, no weather, no shoreline, no living thing of any kind anywhere on or in the planet. The early Earth that existed alongside Theia was itself not yet finished, a magma-covered proto-planet, still accreting mass from the surrounding disk, still glowing with the residual heat of its own violent formation, still in the process of differentiating its interior into the layered structure it would carry for billions of years to come. Its surface, to the extent it had one, would have been largely molten, a roiling, convecting ocean of liquid rock, punctuated by the constant rain of smaller impactors still falling from the debris-rich environment of the inner solar system. Its interior was hot enough that iron was still actively sinking toward the center, still separating from the lighter silicates above it, still carving out the layered structure that would eventually generate the magnetic field that protects life. The Earth and Theia in this period were both works in progress, two incomplete worlds in the same neighborhood, both still being shaped by the same violent forces, both drawing from the same ancient inventory of raw materials. For millions of years they shared that neighborhood, and then, in an encounter that was slow in coming and instantaneous in its violence, they met. Before the collision, before the catastrophe, before the event that would remake both worlds, there was something quieter, a long, slow gravitational arrangement that held Theia in a kind of orbital relationship with the young Earth, one that persisted for millions of years before it finally unraveled. Theia is believed to have occupied one of Earth's Lagrange points, specific regions in space where the gravitational forces at play between two large bodies create pockets of stability, places where a smaller third body can remain in a relatively fixed position relative to the other two without requiring any thrust or propulsion to stay there. In the case of Theia, the two large bodies creating this gravitational pocket were Earth and the Sun. The mathematics of orbital mechanics, first worked out in the 18th century by the French-Italian mathematician Joseph-Louis Lagrange, predict that every two-body gravitational system has 5 such stable or semi-stable points. The two most stable, called L4 and L5, sit along the orbit of the smaller of the two large bodies, 60 degrees ahead of it and 60 degrees behind it. Objects at these points are called Trojan companions, named after the asteroids that share Jupiter's orbit in this way. Theia, in this picture, was something like a Trojan companion to the early Earth, a world that moved through the solar system 60 degrees ahead or behind the Earth in the same orbital path, kept in that relative position by the carefully balanced pull of Earth's and the Sun's combined gravity. For millions of years, that balance held. Two worlds circling the same star, forever separated by the same quiet arc of space, until the balance finally, slowly, irrevocably broke. The concept of Lagrange points is one of the more quietly beautiful ideas in all of orbital mechanics, a recognition that gravity, which we most often experience as a force that pulls things together, can also, in precisely the right configuration, create islands of stability in the otherwise restless and ever-shifting ocean of space. Lagrange points are positions where the gravitational forces of two large bodies combine with the centrifugal effect of a rotating reference frame to produce a point of equilibrium, a location where a smaller object experiences no net force pulling it away from that position. There are 5 such points in any two-body gravitational system. L1 sits between the two large bodies. L2 sits behind the smaller one. L3 sits on the far side of the larger one. These 3 are weakly stable, meaning that an object placed there will tend to drift gradually away if nudged even slightly. L4 and L5, which trail and lead the smaller body by 60 degrees in its orbit, are the genuinely stable ones. Objects placed there tend to return to equilibrium after small disturbances, drawn back by the combined gravitational geometry of the system. We know these points are real and functional because we observe them occupied throughout the solar system. Jupiter has thousands of Trojan asteroids held at its L4 and L5 points. Earth itself has at least one known Trojan asteroid today, co-orbiting with our planet in quiet invisibility. In the early solar system, when the disk of material was denser and the environment far more chaotic, it is entirely plausible and consistent with current models that one of Earth's Lagrange points was occupied not by a small asteroid, but by Theia. There is something almost companionable about the image of Theia and Earth sharing the same orbit for millions of years. Two worlds moving through the early solar system in a slow, synchronized gravitational relationship, neither one able to fully break free of the other, neither one yet close enough for what was, invisibly, already coming. Theia likely shared Earth's orbit in this way for a very long time, millions of years during which the two bodies existed in the same broad neighborhood, separated by the angular distance of 60 degrees, tracing the same elliptical path around the young sun. In the context of the solar system's early history, this kind of shared orbit arrangement was likely not unusual. The density of material in the protoplanetary disk, combined with the gravitational geometry of the Lagrange points, means that growing embryos would have frequently found themselves in exactly such arrangements, orbiting together, gravitationally tethered, drifting in the same slow circuit around the newborn star. What makes Theia's story different is not the arrangement itself, but what eventually happened to it. The slow gravitational dissolution that sent Theia drifting out of equilibrium and toward the most consequential collision in Earth's history. For millions of years before that collision, though, the story was one not of violence, but of proximity. Two worlds in quiet gravitational conversation, separated by the same repeating arc of space, sharing the same year, circling the same star, completely unaware, as worlds are unaware, that their arrangement was already beginning its long, imperceptible unraveling. Nothing in the solar system holds its shape forever, and the stability that kept Theia in its Lagrange point relationship with the early Earth was, by its very nature, a temporary thing. The Lagrange points L4 and L5 are stable in an idealized two-body system, where only Earth and the Sun are exerting gravitational influence on Theia. But the early solar system was not an idealized two-body system. It was a crowded, dynamic environment in which multiple large bodies were exerting gravitational influence on everything else simultaneously. And two of the most significant influences came not from nearby bodies, but from the giants growing farther out in the disk, Jupiter and Saturn. Jupiter, the largest planet in the solar system, was already well formed and massive during the period when Theia occupied Earth's Lagrange point. Saturn, too, was growing rapidly. Both gas giants exerted gravitational influence across enormous distances, their perturbative effects rippling through the inner solar system in the form of resonances and nudges that accumulated over vast timescales. Over millions of years, these gravitational nudges began to destabilize Theia's position. The forces were tiny by human standards, fractions of a meter per second of velocity change over millions of years, influences so small that a single instance would be utterly undetectable. But they accumulated. They reinforced one another in periodic resonances. They pushed and pulled at Theia's orbit with the patient, relentless pressure of deep time until the balance that had held for so long began, very slowly and then increasingly, to tilt. Among all the forces that have shaped the history of the inner solar system, Jupiter's gravity stands in a category of its own. Jupiter is not merely the largest planet orbiting our Sun. It is large enough that its gravitational influence has reached into every corner of the solar system for billions of years, shaping the distribution of asteroids and comets, influencing the orbital evolution of the other planets, and, in the earliest period of solar system history, likely playing a decisive role in the fates of bodies that no longer exist. Jupiter's immense gravity has acted as a kind of gravitational sculptor throughout solar system history, clearing, redirecting and amplifying the effects of orbital interactions across vast distances that no other planet can match. It is believed to have been a key force in eventually dislodging Theia from the stable orbital position it had maintained near Earth's Lagrange point. The mechanism was not sudden. Jupiter did not reach across the solar system and simply knock Theia loose in a single dramatic event. Rather, its gravitational influence created subtle but persistent resonances in the inner solar system, periodic tugs that, each time the orbital periods of the inner bodies aligned in certain ratios with Jupiter's own orbital period, added a small incremental push in the same direction. Over millions of years, those small incremental pushes accumulated into something that the gravitational geometry of the Lagrange point could no longer contain. Theia's orbit began to shift. The equilibrium began to erode, and the path towards the collision that would remake both worlds was already, invisibly, opening. The movement of Theia out of its stable Lagrange position and onto a trajectory that would eventually intersect with Earth's was not sudden. It was not a dramatic shift that happened in a day or a year or even 1,000 years. It was a drift, slow, gradual, almost imperceptible on any human timescale, but inexorable on the timescales that govern the motion of planets. As Theia's orbit became increasingly unstable under the accumulated gravitational perturbations of the outer planets, it began to deviate from the clean, stable arc it had traced for so long. The deviations were tiny at first, small departures from the Lagrange point equilibrium that were partially corrected by the stabilizing forces still acting on Theia from Earth and the Sun, but each correction left a slightly larger residual error than the last. Each partial return to stability still left Theia a little further from where it had been. The orbit grew slowly more eccentric, more elliptical, less circular, which meant that Theia's closest approaches to Earth during each orbit gradually became closer and its furthest departures gradually became more distant. Over millions of years, this slow drift brought Theia's path closer and closer to Earth's own orbit, a narrowing of the gravitational distance between them that, once it began in earnest, had only one possible endpoint. The collision that would create the Moon was not the result of a random accident of trajectory. It was the slow, gravitationally inevitable conclusion of a process that had been building for longer than Earth's current continents have existed in anything like their present form. There is a patience built into the movements of planets that has no true equivalent in the experience of a human life. We measure our time in days and years, in the length of a season, the span of a career, the arc of a lifetime. But the gravitational relationship between Theia and the early Earth unfolded across timescales so vast that they contain millions of our lifetimes within a single chapter. The gravitational relationship between Theia and Earth was not sudden. It was a slow, patient unraveling played out across geological timescales, a word that itself points toward the kind of time in which mountains form and continents drift and oceans fill and drain. To say that Theia's orbit destabilized gradually is to invoke a kind of gradual that has no real equivalent in any experience available to a human being. The perturbations that nudged Theia out of equilibrium might have been accumulating for 20 million years before the collision, a span of time during which, had there been observers watching the sky above the early Earth, nothing would have seemed to be happening at all. The motion of Theia through space would have appeared stable, orderly, serene. The destabilization was written in mathematics, in the slow accumulation of tiny orbital errors, in the long arc of gravitational resonances playing out across timescales that only the universe itself has ever had the patience to work through completely. And this is part of what makes the story of Theia so quietly extraordinary. It is a story that moves at the speed of gravity and the speed of deep time, a process so gradual that it would have been utterly invisible until the moment, finally, when it was not. One of the remarkable things about the giant impact hypothesis, the scientific framework that explains both Theia's existence and the Moon's origin, is how consistently and naturally it emerges from computer simulations of the early solar system, even when those simulations begin from very different starting conditions. Scientists running models of how the inner solar system's planetary embryos would have interacted and evolved over the first 100 million years of solar system history find that Lagrange point companions like Theia appear naturally in many of their simulations. The embryos form, grow, and, in a significant number of simulation runs, find themselves in exactly the kind of stable but temporary orbital arrangement that the giant impact hypothesis requires. And the simulations also consistently show that these Lagrange point companions were inherently temporary, that their stability would erode over tens of millions of years, driven by the accumulated gravitational perturbations of the forming outer planets. The physics that governs these simulations is well established. The parameters are drawn from careful observations of the solar system's current state and worked backward through time using the laws of orbital mechanics. And the result, again and again, is a picture in which bodies like Theia are not unusual but expected, natural products of the early solar system's dynamics, present for a time and then gone, consumed by the very processes of planetary formation that created them. The simulations do not prove that Theia existed, but they demonstrate powerfully that if Theia did exist, and the evidence strongly suggests it did, its eventual destabilization and collision with Earth was not a freak accident. It was what the physics of the early solar system almost inevitably produced, Scientists sometimes describe the period in which Theia and Earth occupied the same orbital neighborhood as a kind of gravitational intimacy, an informal phrase that captures something real about the relationship, even if it requires a certain imaginative generosity to apply it to bodies of molten rock and metal orbiting a young star. But there is something genuine to the idea. Two worlds, formed from the same disk of raw material, sharing the same orbital path around the same star, gravitationally bound to each other for millions of years in a relationship defined by the invisible geometry of mass and distance. There is an intimacy to that, a closeness written not in proximity but in the mathematics of physics. The gravitational field of each body was constantly influencing the other. The tidal forces each exerted on the other, though small at the distances involved, were real and measurable. They moved together through the solar system like companions in an orbital dance that neither had chosen and neither could easily leave. The dance lasted for tens of millions of years. It was quiet and slow and defined entirely by the mathematics of equilibrium, a balance of forces that created stability without closeness, companionship without contact. And then, gradually, the balance shifted. The perturbations accumulated beyond the threshold the system could absorb. The orbit destabilized. The dance began to change its character, from the measured, steady movement of stable companions to the increasingly erratic elliptical approach of two bodies being drawn, by the irresistible and indifferent logic of their combined gravity, steadily and unavoidably toward each other. When we look up at the moon and feel something, wonder or quietude, or the particular comfort of a familiar light in an unfamiliar night, we are, without knowing it, experiencing the distant echo of an event that was not random. The collision between Theia and Earth was not a chance encounter between two unrelated bodies whose paths happened to cross in the vast darkness of space. It was the almost inevitable outcome of the gravitational architecture of the early solar system, a consequence written into the initial conditions of the solar system's formation, waiting to unfold across whatever span of time it required. The orbital dynamics that placed Theia in Earth's Lagrange point, the perturbations from Jupiter and Saturn that slowly eroded that stability, the gradual drift of Theia's orbit toward intersection with Earth's, all of it was the product of physical laws that do not make exceptions and do not show mercy. Given the starting conditions of the early solar system, given the masses and orbital velocities of the bodies involved, given the gravitational influence of the giant planets growing in the outer disk, the collision was, in a meaningful statistical sense, bound to happen. Not necessarily with Theia specifically, and not necessarily at the precise moment it occurred, but a collision of approximately that character between two bodies of approximately those sizes in approximately that region of the inner solar system. The mathematics of the early solar system pointed toward it with something close to certainty. What we see when we see the moon is not the product of chance. It is the product of physics, patient, unhurried, working itself out across billions of years without haste or hesitation. There are events in the history of a world that are so large, so catastrophic, so total in their consequences, that nothing that comes after them is untouched by what happened. The landscape of all that follows is defined by that single event, shaped by it at every scale, from the deepest interior of the planet to the face of its moon, to the length of its days and the tilt of its axis. For Earth, that event is the giant impact. The collision between Theia and the early Earth is known in science as the giant impact, sometimes also called the Big Splash, and it holds a place in planetary science that is almost without parallel. It is considered the most significant collision in Earth's history, the event that ended one world and fundamentally remade another. The giant impact was not simply a large meteor strike scaled up in magnitude. It was a collision between two planetary bodies with differentiated interiors, with cores and mantles, with gravitational fields substantial enough to have shaped the space around them for millions of years. It was, in every meaningful sense, the end of Theia as an independent world and the beginning of Earth as the planet we know. The moon in your sky is the monument to this event. The tides that move your oceans are its gravitational inheritance. The seasons that mark your year are a consequence of it. The magnetic field that protects life on this planet may have been strengthened by it. Everything, every single feature of the world that surrounds you tonight, traces some thread of its existence back to that one ancient, irreversible collision. To place the giant impact in time is to confront the almost incomprehensible depth of the past. The collision between Theia and the early Earth is estimated to have occurred approximately 4.5 billion years ago, roughly 50 to 100 million years after the solar system first formed from its rotating cloud of gas and dust. In human terms, 4.5 billion years is a number that escapes ordinary comprehension. If the entire history of the universe since the Big Bang were compressed into a single calendar year, the giant impact would have occurred in late February, before the first fish ever swam in any ocean, before the first tree ever grew from any soil, before the first living cell ever divided in the warm chemistry of any ancient sea. The age of the dinosaurs, which feels ancient and remote to us, would be a single day in that compressed calendar. All of human civilization, every city, every story, every scientific discovery, every monument ever built, would occupy less than the final 2 minutes of the final day of the year. And yet, even at 4.5 billion years old, the giant impact occurred after something. It occurred after tens of millions of years during which the solar system had already been forming, after Theia had grown and evolved and settled into its long orbital relationship with Earth, after Earth itself had already begun to differentiate and develop its complex interior structure. The universe had already been old for a very long time when Theia finally struck. The story of the giant impact is the story of the very beginning of our world. But even that beginning came late in the universe's long and patient history. The geometry of a collision at planetary scale matters enormously, not just for the immediate drama of the moment, but for everything that follows from it across the billions of years that come after. Had Theia struck the early Earth head-on at a direct perpendicular angle to its surface, the outcome would have been catastrophically different from what the evidence suggests actually occurred. A perfectly direct impact of two planetary bodies, one Mars-sized and one Earth-sized, would most likely have resulted in a merged object of combined mass, releasing enormous energy as heat but not producing the large quantity of material thrown into orbit that would eventually become the Moon. Instead, what the physics and the accumulated evidence point toward is something more oblique, a glancing blow, a collision at an angle rather than straight on, more like the strike of a billiard ball off the cushion than the direct collision of two objects meeting face to face. At the moment of impact, Theia struck the early Earth at a glancing angle, not head-on but at an oblique trajectory that sent much of the combined material streaming off into orbit around the surviving merged body rather than simply adding to it directly. This glancing geometry was essential to everything that followed. It was what allowed enormous quantities of vaporized and molten rock to be ejected into the space around Earth, what gave that debris the angular momentum needed to remain in orbit rather than simply falling back to the surface, and what ultimately provided the raw material from which the Moon would eventually form. The angle of Theia's final approach is the detail that shaped everything. Among the many details that emerge from scientific modeling of the giant impact, the estimated angle of Theia's approach is one of the most consequential and one of the most carefully studied. The impact angle is estimated to have been approximately 45 degrees, a detail that does not emerge from any direct observation, since no observation of the event is possible from this distance in time, but from the painstaking reverse engineering of its aftermath. Scientists working on the giant impact hypothesis use computer simulations that model what a collision between two planetary bodies of given masses, traveling at given velocities, at a given angle, would produce in terms of the resulting debris field and the characteristics of the merged surviving body. They then compare those simulated outcomes to the real Moon as it actually exists, its mass, its orbital characteristics, its chemical composition, its angular momentum relationship with Earth, and work backward to identify which impact parameters most closely reproduce what is actually observed. The 45-degree angle emerges repeatedly from these analyses as one of the best fits to the available constraints. At that angle, the impact delivers enough energy to vaporize enormous quantities of rock from both bodies, enough angular momentum to the ejected material to keep it in a stable orbit rather than having it fall back to the surface, and enough directed force to blend the outer layers of Theia and early Earth into the mixed debris cloud from which the Moon would eventually condense. It is a remarkably specific detail to recover from an event that happened 4.5 billion years ago, a testament to the power of physics-based reasoning and the information preserved in the Moon's own structure. The velocity at which Theia struck the early Earth is one of those details that the mind struggles to fully absorb, not because the numbers are impossibly large by astronomical standards, but because they sit at a precise threshold where our ordinary intuitions about the behavior of matter simply stop applying. Theia struck Earth at a speed estimated between 4 and 20 kilometers per second, a range that reflects genuine uncertainty in the exact orbital parameters of Theia at the time of the collision, parameters which no observation can now precisely constrain. To put that range in a familiar context, a passenger aircraft travels at roughly 0.25 kilometers per second. A rifle bullet travels at roughly 1 kilometer per second. The fastest spacecraft humanity has ever launched moved at a small fraction of the lower end of Theia's estimated impact velocity. But what matters about these velocities is not how they compare to human-made objects. It is what they do to matter at the moment of impact. At 4 to 20 kilometers per second, rock and metal do not behave the way we ordinarily experience them. The timescale of the collision is shorter than the timescale required for solid material to respond to stress through its normal mechanical properties, shorter than the time it takes for a sound wave to cross the body of the impacting object. The result is that the impacting and impacted materials both behave more like fluids than solids, flowing, splashing, merging and separating, before the energetics of the event vaporize vast portions of both bodies entirely, converting solid rock into superheated gas in a transformation that was over at the scale of the individual impact zones in a matter of seconds. What happened to the material of Theia and the outer layers of early Earth in the moments of the giant impact is one of the most extraordinary transformations of matter in the history of this solar system. A transformation that challenges every ordinary assumption about what rock is and what it can become. At the velocities and pressures involved in the collision, the impacting material did not simply shatter or melt or liquefy in any ordinary sense. At those velocities, both Theia and the outer layers of early Earth were vaporized, not merely shattered but converted into a superheated cloud of rock vapor and molten droplets, a state of matter that sits somewhere between the liquid and gaseous phases at temperatures and pressures that exist on Earth today only in the most extreme laboratory conditions, and that existed naturally in the moments after the giant impact on a scale that encompassed an entire planet. Rock vapor. The phrase is almost surreal, a reminder that rock, which we experience as the very definition of solidity and permanence, is only solid because of the specific temperature and pressure conditions that prevail at Earth's familiar surface. Change those conditions dramatically enough and the distinction between rock and gas dissolves along with everything else. The material that had been Theia's mantle and the material that had been Earth's outer layers were both reduced to the same superheated, glowing, slowly expanding cloud of vaporized mineral, a cloud hot enough that its atoms had enough energy to move freely in all directions, hot enough that the distinction between the two worlds from which it came was being erased at the atomic level. Out of that cloud, eventually, the moon would slowly and patiently form. The energy released in the giant impact sits at a scale that human language was not designed to convey, a scale at which comparisons to familiar things become almost meaningless, and yet must be attempted simply to give the mind some foothold in the enormity. The energy released in the giant impact has been estimated as equivalent to billions of nuclear weapons detonating simultaneously, a comparison that sounds hyperbolic but is, if anything, an understatement when considered in the full context of what the impact actually accomplished. It converted enormous volumes of solid rock into vapor. It accelerated enough material to orbit-forming velocities to eventually assemble an object the size of the moon. It permanently altered the rotation rate and axial tilt of an entire planet. It melted the surface of the Earth to a depth of hundreds of kilometers and generated heat that persisted for thousands of years afterward. Every one of those consequences required energy, enormous, sustained, planet-reshaping quantities of energy, and all of it came from the kinetic energy of Theia's final approach, converted in the violence of impact into heat and light and motion. We experience the human scale of energy in terms of calories and kilowatts and the fuel burned by engines. The giant impact operated at a scale that encompasses all of those things and all of human energy consumption across all of recorded history and renders them invisible, too small to register against the magnitude of what happened when Theia struck. It was an event that operated at the energy scale of planetary formation itself because that is precisely what it was, the final and most dramatic act in the formation of the world we inhabit. There is a strange and almost philosophical disproportion between the brevity of the giant impact as an event and the permanence and reach of its consequences. The collision lasted only a matter of hours in terms of the actual impact event, the literal process of Theia's body contacting Earth's, the deformation and vaporization of both bodies' outer layers, the ejection of material into orbit, the initial merger of the two iron-rich cores. On the timescale of planetary history, this is less than an instant, a flash so brief that if the 4.5 billion years since the impact were compressed into a single calendar year, the impact itself would occupy less than a single second of that entire year. And yet, from those hours of violent contact came consequences that have unfolded continuously for every moment of the 4.5 billion years since. The moon's formation, the moon's gradual recession from Earth, the tides, the stabilization of Earth's axial tilt, the long slowing of Earth's rotation, the seasonal cycle that gives the world its rhythm of growth and rest, perhaps even the conditions that made life possible. The brevity of the cause and the depth and permanence of its effects sit in a relationship that has no good parallel in ordinary human experience. The giant impact is a reminder that at planetary scale, a few hours can contain enough change to define the next 4.5 billion years. That a single event can reach forward in time and shape everything that follows it for as long as the world exists. One of the most significant details of what happened during and immediately after the giant impact concerns not what was ejected into space, but what remained, specifically what became of Theia's iron-rich core once the collision was complete. When two planetary bodies collide at planetary scale and velocities, the fate of their metallic cores is determined by a combination of the impact geometry, the energy of the collision, and the fundamental law that governs the behavior of materials of different densities under the influence of gravity. In the case of the giant impact, most of Theia's iron core is believed to have sunk into and merged with Earth's own core during or shortly after the impact. Iron is among the densest materials in a rocky planet's interior. During the collision, as the outer layers of both Theia and Earth were vaporized and blasted outward, the denser metallic core material of both bodies was subject to the same gravity that always causes the heaviest things to sink. And in the chaos of the post-impact world, with Earth's interior radically disturbed and partially remolten throughout its depth, Theia's iron found its way downward through the molten rock, sinking through layers of silicate liquid and merging with Earth's already forming iron core into a single combined metallic heart. The iron that generates Earth's magnetic field, that shields all life on this planet from the full force of the solar wind, that makes compasses point north and that anchors the navigation of every migrating bird. Some of that iron was once, 4.5 billion years ago, the core of another world entirely. While Theia's iron core was sinking into the Earth, the fate of its outer layers, the rocky mantle of silicate minerals that had surrounded that core throughout Theia's existence, was being decided by a completely different set of physics. Where dense iron is pulled inward by gravity, lighter rock responds differently to the energy of a high-velocity impact. It is blasted outward. The outer layers of Theia, its rocky mantle, were ejected into space during the collision, blasted free from their original context and sent streaming outward in a vast debris field of vapor and molten rock and shattered rock fragments, mixing as they traveled with the vaporized and ejected outer layers of Earth's own mantle. This mixing is deeply important to understanding what the moon is made of. By the time the debris left the immediate environment of the collision and began to distribute itself into a disk around the surviving merged Earth, it was already chemically blended. Theia's mantle material and Earth's mantle material intermixed at a level that could not easily be distinguished one from the other. It was no longer Theia's rock and Earth's rock held separately. It was a shared, superheated, mixed debris cloud from which the moon would eventually form. This mixing explains why moon rocks are chemically so similar to Earth rocks, because the moon formed from the blended debris of both worlds' mantles, combined with the fact that Theia and early Earth were themselves chemically similar to begin with, having formed from the same region of the same proto-planetary disk. The moon is, in every chemical sense, the child of both. In the immediate aftermath of the collision, the space around the shattered, combined remnant of Theia and early Earth was not empty. It was filled, utterly and densely filled, with the material of two destroyed worlds, still hot enough to glow with their own light, still moving with the angular momentum imparted by Theia's oblique impact, still in the process of deciding what they would become. The debris ejected into space formed a vast, hot disk of material encircling the early Earth, a structure that planetary scientists sometimes compare in its basic geometry to the rings of Saturn, though in almost every other characteristic it was radically different from those cold, thin rings of ice and rock. Saturn's rings are relatively sparse, cold, and made primarily of ice and rock, the product of tidal disruption rather than planetary collision. The disk that formed around post-impact Earth was thick and dense and ferociously hot, made of vaporized and molten rock, carrying enormous quantities of angular momentum and containing within it enough mass to eventually assemble a body roughly the size of the Moon. The comparison to Saturn's rings is useful only as a way of invoking the basic image, a disk of material in orbit around a planet, confined within a certain orbital range, coherent enough to have structure. Beyond that geometric similarity, the two phenomena are almost nothing alike. The debris disk around post-impact Earth was one of the most energetically extreme environments in the history of the inner solar system, a churning, glowing, slowly cooling ring of former planet substance, beginning the long, gradual process of deciding what it would become. The debris disk that formed around post-impact Earth was not simply chaotic material scattered into orbit without structure or purpose. It was a disk with specific physical properties, a specific mass distribution, a specific total angular momentum, a specific range of orbital radii within which it was gravitationally confined, and those properties determined everything about what it would eventually become. The debris disk is estimated to have contained enough material to assemble a body roughly the size of the Moon, which is precisely what eventually happened. This is one of the most elegant aspects of the giant impact hypothesis. It makes a specific, quantitative prediction about the mass of material that should be in orbit after the collision, and that predicted mass closely matches the actual mass of the Moon as we observe it today. The Moon is not merely approximately the right size for this hypothesis to work. It is approximately exactly the right size, a match between theoretical prediction and direct observation that gives scientists significant and well-founded confidence that the giant impact hypothesis is pointing at something real. The disk's total mass, its angular momentum, its chemical composition, all of these properties are the consequences of a specific collision between bodies of specific sizes at a specific angle and velocity. And all of them point toward the same event, the same collision, the same lost world. Theia is the hypothesis that explains all of the constraints simultaneously, the only known model that can account for the Moon's size, composition, orbital characteristics, and chemical similarity to Earth all at once in a single coherent story. The environment in the immediate aftermath of the giant impact was unlike anything that exists anywhere in the inner solar system today. A world so extreme in its temperature and energy that the very concept of a solid surface had ceased to apply. The temperature of the debris disk immediately after the impact was extraordinary. Rock existed as vapor, and the environment around early Earth glowed with an almost unimaginable heat, a planet wrapped not in atmosphere but in the luminous, slowly dispersing cloud of its own vaporized surface. The temperatures in the immediate post-impact environment exceeded anything that Earth experiences today, even in its deepest volcanic chambers or its hottest laboratory experiments. At the surface of the post-impact Earth itself, what had been solid rock was now a global ocean of liquid magma, and above that magma ocean rose a thick, glowing atmosphere of rock vapor and mineral gases, silica and magnesium and iron and all the other components of planetary rock, existing in a gaseous state for which there is no counterpart anywhere in the world that exists today. Higher up, in the disk of debris in orbit around the Earth, conditions were similarly extreme, temperatures that would slowly fall over thousands of years as the disk radiated its heat away into space and the vaporized rock gradually condensed into liquid droplets and then into solid fragments. In those slowly cooling fragments, the Moon was beginning, grain by patient grain, to find its shape. Among the many consequences of the giant impact, one that is often overlooked in the drama of what was added to Earth, the Moon, the new axial tilt, the faster spin, is the significance of something that was subtracted. The giant impact is thought to have stripped away most of Earth's original atmosphere. The gases that had accumulated before the collision were largely lost to space in the violence of the event. Earth, before the collision with Theia, had been accumulating gases for tens of millions of years. The process of planetary formation, with its ongoing volcanic outgassing and the delivery of volatile-rich material from infalling planetesimals, had provided the early Earth with a growing inventory of gases, primarily hydrogen and helium at first, supplemented by heavier volatiles like water vapor, carbon dioxide, and nitrogen as the planet grew. This proto-atmosphere was the Earth's first envelope, its first effort at holding something above its rocky surface. But the energy of the giant impact was sufficient not just to vaporize the surface rocks, but to accelerate a significant fraction of the atmosphere to or beyond escape velocity. The speed at which a gas molecule moving away from Earth's surface cannot be pulled back by gravity and instead continues into space forever. This atmospheric stripping reset much of the chemical inventory of the early Earth's surface environment. The atmosphere we breathe today, the nitrogen and oxygen that sustain life, the water vapor in the clouds, is largely a secondary atmosphere, built up after the giant impact from volcanic outgassing and the delivery of fresh volatile material by the ongoing arrival of comets and asteroids in the subsequent billions of years. Beyond the Moon itself, the most enduring physical legacy of the giant impact may be written in something as simple and as ever-present as the turning of a day. The rotation of the Earth, the spin that moves the sun across our sky, that divides our experience of time into light and darkness, that governs the rhythm of our waking and our sleeping and every daily cycle of the natural world, was profoundly and permanently altered by the collision with Theia. Before the impact, Earth rotated at a certain rate, the details of which are not precisely known, but which was almost certainly much slower than what came after. Theia's impact also significantly altered Earth's rotation. Before the impact, Earth rotated more slowly. After, it spun dramatically faster, with some models suggesting a single day lasted as little as 2 to 5 hours. A world spinning so fast that sunrise to sunrise again occupied only a few hours. The centrifugal forces at the equator would have been dramatically stronger. The atmosphere whipped into circulation patterns that have no analogue in any climate that has existed since. The tidal forces between Earth and the newly forming Moon intense beyond any comparison to the gentle tides we experience today. That extreme spin has been slowing down continuously ever since, gradually braked by the tidal friction between Earth and the Moon, a process that continues today at a measurable rate, adding tiny fractions of a second to each day over geological timescales. The day you have just lived through, 24 hours long, is the length it is because of Theia, and because of 4.5 billion years of the Moon's patient gravitational work since. Of all the physical properties that the giant impact bequeathed to the Earth, perhaps the most consequential for the long-term development of life on this planet is one that most of us experience every year without ever considering its origin. The tilt of Earth's axis, the angle at which our planet leans relative to the plane of its orbit around the Sun, is what gives us our seasons. When the northern hemisphere tilts toward the Sun, it receives more direct sunlight and longer days, and we call it summer. When it tilts away, it receives less direct sunlight and shorter days, and we call it winter. The tilt is not a large angle by astronomical standards, approximately 23.5 degrees, but it is large enough to create the seasonal cycle that has shaped the evolution of almost every multicellular organism on this planet, that has driven the migration of species across continents, the cycles of agriculture across thousands of years of human civilization, and the variation in climate that has alternately expanded and contracted ice sheets and forests and grasslands across hundreds of millions of years. The impact tilted Earth's axis to approximately 23.5 degrees, a consequence of the angular momentum delivered by Theia's oblique strike. Theia set the tilt. From that tilt came seasons. From seasons came the selection pressures that drove the evolution of plants and animals adapted to cyclical change. From those selection pressures came, eventually, among everything else, the biological diversity of the world you inhabit, and the human species that learned to read the seasonal signals written in the migration of birds and the flowering of trees. In the aftermath of the giant impact, the surface of the Earth was a place that bears almost no resemblance to anything on the world that sits beneath your feet tonight. There was no crust. There was no solid ground of any kind anywhere on the planet. In the aftermath of the impact, Earth's surface was entirely molten, a global magma ocean covering the planet to depths of hundreds of kilometers, a roiling, convecting, luminous sea of liquid rock that stretched without interruption across the entire surface of the world from pole to pole. The phrase global magma ocean is one of the most extraordinary descriptions in all of planetary science, and it is entirely accurate. The energy deposited by the giant impact was sufficient not just to melt the surface layers of Earth, but to melt the planet to substantial depth, creating an ocean of liquid rock so deep and so total that the concept of a surface in any ordinary sense had ceased to apply. Above this glowing magma ocean rose the thick rock vapor atmosphere that the impact had generated, a blanket of mineral gas that would take thousands of years to cool and condense, gradually raining silicate droplets back down onto the still molten surface below. Below the magma ocean, Earth's iron core was already solid or beginning to solidify, having differentiated out from the rest of the planet's material before the impact and now reassembling itself at the center of the merged world. But the vast middle region, everything between the core and the vaporized upper atmosphere, was liquid rock, convecting in enormous, slow swirls, patiently carrying heat from the deep interior up to the surface where it could slowly radiate away into the cooler rock vapor above. Heat does not disappear quickly from a world the size of Earth, especially when that heat has been deposited in the quantities that the giant impact delivered. The thermal energy left behind in the Earth by the collision was so enormous, and the mechanisms by which the Earth could radiate that heat away into the cold of space so limited that the cooling process was necessarily very slow, stretched across thousands to perhaps tens of thousands of years before the global magma ocean began to develop anything resembling a persistent solid surface. The cooling was not uniform across the planet. The surface of the magma ocean, exposed to the slightly cooler environment above it, would have cooled most quickly, forming thin, temporary crusts of solidified rock that would then be broken and remelted as hotter material welled up from below through convection. This is similar to the way lava flows cool on their surfaces while remaining molten beneath. But imagine this process repeated endlessly across the entire surface of the world for thousands of years. Gradually, as the total heat content of the planet diminished through radiation, the thin temporary crusts became thicker and more persistent, until eventually the first true solid surface began to form. Patchy at first, unstable, easily remelted by the continuing heat from below, but growing steadily thicker and more continuous as the long cooling continued. Earth was finding its skin, and on the Moon, forming just above in the slowly cooling debris disk, the same process of condensation and solidification was also beginning. Two worlds, born of the same catastrophe, slowly and separately becoming solid for the very first time. The formation of the Moon from the debris disk that surrounded post-impact Earth is one of the most remarkable processes in the history of the solar system, and one of the fastest by the standards of how worlds are ordinarily assembled. Planetary accretion, as it normally proceeds across the proto-planetary disk, is a patient process that unfolds across tens to hundreds of millions of years as dust accumulates into pebbles, pebbles into boulders, boulders into embryos, embryos into planets. The Moon did not have the luxury of that leisurely timescale. The Moon is believed to have assembled from the debris disk in a relatively short amount of time. Current models suggest it may have formed within decades to a few thousand years after the impact. The reason for this dramatically accelerated timescale is the density of the debris disk itself. Unlike the relatively sparse disk of material from which the planets formed over millions of years, the debris disk around post-impact Earth was extraordinarily dense, packed with enough material in a relatively small volume that gravitational interactions between the fragments were constant, frequent, and powerful. Clumps formed quickly. Small clumps attracted nearby material and grew into larger clumps with stronger gravity. Larger clumps accumulated surrounding debris at an accelerating rate. The Moon was not assembled slowly, grain by grain, in the patient manner of ordinary planetary formation. It was assembled in something closer to a gravitational avalanche, a rapid accumulation that built a moon-sized object in what was, by the standards of the solar system, almost an instant. The Moon that emerged from this process was not the cool and familiar satellite we know today. It was an infant world, molten and glowing, new in every sense. The process by which the Moon formed from the debris disk is called accretion, the same fundamental mechanism that built every rocky planet in the solar system. and indeed the same process that built Theia and the early Earth themselves before their collision. But the moon's accretion was a compressed and intensified version of that process, driven by the extreme conditions that the giant impact had created. In normal planetary accretion, the timescale is set by the low density of the protoplanetary disk and the enormous distances between the growing bodies. There is simply not much material in any given volume of space, and the growing embryos are spread across vast orbital ranges that require millions of years to sweep clean. In the debris disk around post-impact Earth, both of those constraints were dramatically changed. The material was concentrated into a much smaller orbital range. The density of the disk was orders of magnitude higher than the normal protoplanetary disk from which the planets formed. In this environment, accretion did not proceed at the measured pace of normal planetary formation. It proceeded at the pace dictated by the density of available material and the efficiency of gravity in drawing that material together, and those two factors combined to build the moon with extraordinary speed. The moon that emerged from this process was recognizably a world. It had mass, it had gravity, it had a structure already beginning to differentiate. But it was a world in the most raw and formative sense, still glowing, still incorporating the last fragments of the debris disk, still finding its final shape in the gradual quieting of the post-impact environment. One of the details about the early moon that most powerfully conveys how different our satellite's earliest existence was from its present state concerns not its composition or its temperature, but its distance from the world it orbits. How close it was in the immediate aftermath of its formation to the Earth it now circles from nearly 400,000 kilometers away. The moon formed much closer to Earth than it is today. Immediately after its formation, the moon may have orbited at only 20,000 to 30,000 kilometers away, compared to its current distance of approximately 384,000 kilometers. The difference is staggering. At 20,000 to 30,000 kilometers distance, the moon would have appeared enormous in the Earth's sky. Not the modest silver disk we see tonight, comfortable and familiar at its great distance, but a vast looming presence perhaps 15 times wider in apparent diameter, close enough that its gravitational pull on Earth's still liquid surface would have raised enormous tidal bulges in the global magma ocean below. The tidal forces between the newly formed moon and the newly formed post-impact Earth at that distance would have been staggering, orders of magnitude more powerful than the tides the moon raises in today's oceans. Those powerful tidal forces would have generated immense heat through friction in Earth's interior, and they would also have been the very forces that began the moon's long outward journey, the same tidal dynamics that continue today at the modest rate of 3.8 centimeters per year to push the moon slowly and steadily farther from Earth. The moon that formed from the giant impact's debris disk was not a cold, quiet world. It was a world that, in its earliest existence, burned with the residual heat of the catastrophe that had created it. When the moon first formed, it too was covered in a global magma ocean. Its surface was entirely molten, glowing with residual heat from the accretion process that had built it, a mirror in miniature of the same fiery state that Earth itself was experiencing in the same geological moment. The heat came from multiple sources simultaneously. The gravitational potential energy of all the material that had fallen inward during accretion was converted to thermal energy as it impacted the growing moon's surface, adding heat with every collision. The tidal friction between the moon and the still rapidly spinning Earth generated additional heat in the moon's interior, as the gravitational flexing of the body repeatedly stressed and relaxed the rock within it. The decay of short-lived radioactive isotopes, the same heat sources that had contributed to melting the interiors of the early Earth and Theia themselves, was ongoing within the moon's own newly formed rock. All of these heat sources combined to produce a world that, in its earliest existence, had no solid surface whatsoever, a globe of liquid rock covered by a magma ocean comparable in its basic character to the one that covered post-impact Earth at precisely the same time. Two worlds in this earliest period were mirrors of each other, both molten, both slowly cooling, both separately beginning the long process of finding their solid selves. As the moon's global magma ocean slowly lost its heat to the cold of space, the material within it began to solidify, but not all at once and not uniformly throughout. The cooling of a magma ocean on a planetary body proceeds according to the mineral chemistry of the molten rock and the specific conditions of temperature and pressure at different depths within the body. In the Moon's case, as the magma ocean cooled over tens of millions of years, the heavier minerals that crystallized at high temperatures, dense iron and magnesium-rich silicates, sank toward the base of the magma ocean, forming the beginnings of the lunar mantle. The lighter minerals, primarily a mineral called plagioclase feldspar, which is rich in calcium and aluminum and significantly less dense than the other minerals crystallizing at the same time, floated. They rose to the surface of the cooling magma ocean like foam forming on the surface of a cooling liquid, accumulating in a thick layer of light-colored, low-density rock across the entire surface of the Moon. This floating layer of plagioclase-rich rock is what became the lunar highlands, the pale, heavily cratered regions that form the dominant visual texture of the Moon's surface as seen from Earth. They are among the oldest solid surfaces in the solar system, preserved from the moment billions of years ago when the Moon first stopped being a liquid world and started being a solid one. When you look at the pale swathes of the lunar highlands, you are looking at the cooled surface of the Moon's very first solid skin, ancient beyond any ordinary reckoning. The light-colored regions of the Moon's surface, the lunar highlands, are not simply old. They are ancient in a sense that encompasses a meaning far larger than most of us are accustomed to applying to the word. The lunar highlands are among the oldest solid surfaces in the solar system, direct relics of the Moon's magma ocean cooling, formed in the first 100 million years of the Moon's existence and preserved on the surface essentially ever since. On Earth, nothing like this exists. Earth's surface is geologically active, constantly renewed by plate tectonics, volcanic resurfacing, erosion by wind and water, and the continuous cycling of crust back into the mantle and out again. The oldest mineral grains found on Earth's surface are only approximately 4.4 billion years old, and they are vanishingly rare. The lunar highlands are substantially older, dating back in their formation to a time when Earth's own surface was still a magma ocean, before the first solid crust of any kind had formed anywhere on our planet. The highland rocks have survived not because they are indestructible, but because the Moon has no plate tectonics, no liquid water, no significant atmosphere, and very limited geological activity of any kind. The only process that significantly modifies the lunar surface is the constant rain of meteorite impacts, which has pulverized and mixed the surface material over billions of years, but has not fundamentally replaced the rock beneath. The highland material is the same material that crystallized from the original magma ocean. It is, in a very real sense, the Moon's first solid skin, and it has been there unchanged in its essential character ever since. The dark regions of the Moon's surface, the broad, flat, shadowy plains that fill in the basins of large ancient craters and give the Moon its characteristic face, tell a different part of the story. A later chapter written not in the cooling of the original magma ocean but in the volcanic activity that followed hundreds of millions of years afterward. These regions are called Maria, from the Latin word for seas, a name given to them by early telescopic observers who, seeing their flat, dark expanses through the newly invented telescope in the early 17th century, imagined them as actual bodies of liquid water spread across the surface of a world much like our own. They are not seas of water, they are ancient lava plains, vast sheets of solidified basaltic lava that flooded low-lying regions of the lunar surface during the period between approximately 3 and 4 billion years ago, long after the original magma ocean had cooled and solidified. The Maria formed when large meteorite impacts punctured the Moon's solidified crust, allowing the still warm interior to well up and flood the resulting basins with dark, iron-rich lava. When that lava solidified, it created the broad, smooth plains we observe today. The patterns those dark plains make against the pale highland background, the face in the Moon, the rabbit in the Moon, the different shapes different cultures have seen in the Moon's surface across thousands of years of human looking, are the product of 4 billion years of geological history written in the contrast between ancient highland rock and younger lava. Every story ever told about the face of the Moon was inspired by a geological record stretching back almost to the beginning of the solar system itself. The internal structure of the Moon, what it is made of, how its materials are distributed from center to surface, carries within it the unmistakable signature of its origin in the giant impact. written not in any single measurement, but in the overall pattern of the Moon's physical properties as a world. The Moon's interior is far less dense than Earth's interior, a direct consequence of its origin in the outer rocky layers of Theia and early Earth, rather than their iron-rich cores. This difference in internal density is fundamental, measurable, and deeply informative. Earth's average density is approximately 5.5 grams per cubic centimeter, a reflection of the fact that Earth has a large, heavy iron core at its center, surrounded by a rocky mantle of somewhat lower density. The Moon's average density is approximately 3.3 grams per cubic centimeter, much closer to the density of rocky silicate minerals alone, without the substantial contribution of a large iron core. This lower average density tells us something specific about where the Moon's material came from. If the Moon had formed by any mechanism that included significant contributions from the iron-rich cores of the bodies involved in its formation, it would be denser than it is. The fact that it is not, the fact that the Moon's density is consistent with its being made primarily of rocky mantle material rather than metallic core material, is one of the strongest lines of evidence for the giant impact hypothesis. The impact ejected the outer rocky layers of Theia and Earth into orbit. The core material stayed behind. The Moon is what you get when you build a world from mantle rock alone. The Moon's small iron core, one of its most structurally distinctive characteristics, is both a direct consequence of its origin in the giant impact and a feature that makes it fundamentally different in character from Earth and the other terrestrial planets of the inner solar system. The Moon has a very small iron core relative to its total size, estimated at only 1 to 2% of its total mass, compared to Earth's core, which accounts for about 30% of Earth's mass. This is a striking and meaningful difference. In the other terrestrial planets, Mercury, Venus, Earth, and Mars, iron cores make up a substantial fraction of the total mass, because all of those planets formed through processes that included the mixing of metal-rich and rock-rich material over long periods of gradual accretion from the protoplanetary disk. The Moon formed differently. It formed from material that had already been through the differentiation process inside Theia and early Earth. Material from the outer rocky mantles of those bodies well after the heavy iron had already separated and settled to their cores. When that mantle material was ejected into orbit by the giant impact and accumulated into the Moon, it was already depleted in iron by the prior differentiation of its parent bodies. The small iron core the Moon does possess, enough to have generated a weak magnetic field early in its history, though that field has since decayed, is thought to be the product of a small amount of iron-rich material that was mixed into the debris disk during the most intense moments of the impact. It is a trace, a minor footnote in the Moon's composition. But it is there, deep in the Moon's interior, a small metallic heart in an otherwise thoroughly rocky world. Among all the lines of evidence that support the giant impact hypothesis, one of the most compelling is written not in the gross physical properties of the Moon, its size, its density, its orbital characteristics, but in the chemistry of its rocks at the level of individual minerals and their atomic compositions. The composition of the Moon is strikingly similar to Earth's outer mantle, further evidence that it formed from material blasted off Earth's surface during the giant impact. This compositional similarity extends across a wide range of chemical measurements. The ratios of different mineral compounds in Moon rocks closely match the ratios in rocks from Earth's mantle. The types of silicate minerals present in both are broadly similar. The depletion in iron and other heavy metals in the Moon's overall composition corresponds to the excess of iron in Earth's core, as if the two together represent the partitioned inventory of the original bodies involved in the impact, one receiving the metal, the other receiving the rock. This chemical similarity was not expected from any of the competing hypotheses for the Moon's origin that existed before the giant impact theory was developed and refined. If the Moon had formed by fission from a rapidly rotating Earth or by capture from elsewhere in the solar system, its chemical signature would look different in specific and testable ways. Only the giant impact hypothesis naturally accounts for the Moon's deep chemical similarity to Earth's mantle, because in that scenario the Moon literally is Earth's mantle, or most of it combined with what remained of Theia's, blasted into orbit and reassembled into a new world. When the Apollo astronauts returned to Earth from their missions to the Moon between 1969 and 1972, they brought with them something more scientifically valuable than almost anything else they could have carried in their sample return capsules. Rocks. Moon rocks. Actual physical samples of the lunar surface, collected by human hands from the surface of another world for the first time in the history of our species, brought back to Earth's laboratories where they could be subjected to the full power of modern analytical chemistry. Among the many things that scientists learned from the detailed analysis of those samples, one of the most profound and most consequential concerns a specific chemical measurement called oxygen isotope ratios. Moon rocks brought back by Apollo missions share nearly identical oxygen isotope ratios with rocks from Earth, a chemical fingerprint that strongly supports the giant impact hypothesis. Oxygen is the most abundant element in the rocky bodies of the inner solar system, and it comes in several different isotopic forms, atoms of oxygen that differ from each other in the number of neutrons in their nuclei. The ratio in which these isotopes are present in any given rock is a kind of chemical address, a signature that reflects where in the solar system the material that formed that rock originated. Bodies from different parts of the solar system have measurably different oxygen isotope ratios. Mars has its own characteristic signature. The asteroid belt has its own. Earth has its own very specific signature. And the fact that moon rocks share that same signature to a remarkable degree of precision tells us something important and powerful about where the moon's material actually came from. The significance of the oxygen isotope similarity between Earth rocks and moon rocks cannot be overstated in the context of the scientific case for the giant impact hypothesis. In planetary science, oxygen isotope ratios serve as a kind of chemical fingerprint for the specific region of the solar system in which a body formed. They reflect the particular mix of materials that were present in that region of the protoplanetary disk, and they are sufficiently different between different regions that scientists can use them to identify where meteorites originated, to distinguish Martian meteorites from asteroid meteorites and from cometary material, and to trace the histories of planetary bodies across the solar system. The similarity in oxygen isotopes between Earth and moon rocks was one of the key pieces of evidence that convinced the scientific community the giant impact hypothesis was correct. Before the Apollo samples were analyzed in detail, many scientists expected that if the moon had formed from a separate body that had impacted Earth, a body that presumably formed in a different part of the solar system or at a different time, its oxygen isotope ratios would be measurably different from Earth's own signature. The fact that they are instead nearly identical was both surprising and deeply informative. It tells us that the material from which the moon formed was chemically almost indistinguishable from the material of Earth's outer layers, consistent with the hypothesis that both Theia and Earth formed from the same region of the same protoplanetary disk, and that the moon assembled from a blended mixture of both bodies' material that was chemically similar to Earth before the collision and thoroughly mixed during it. There is a quietness to the moon today that stands in stark contrast to its violent origin, a geological stillness that reflects billions of years of cooling and the gradual exhaustion of the internal heat that once drove its activity. The moon is geologically quiet today compared to Earth. It has no active plate tectonics and very limited ongoing volcanic activity, a consequence of its smaller size and the faster cooling that smaller size inevitably produces. Plate tectonics, the process by which Earth's outer shell is divided into moving plates that collide and separate and slide past each other, driving mountain building, ocean formation, and the cycling of surface material back into the deep interior, is ultimately powered by the heat of Earth's interior. That heat powers the slow convection of the mantle, and that convection in turn drives the movement of the overlying tectonic plates. Earth, being larger than the moon and possessing a larger inventory of heat-producing radioactive elements, has maintained enough internal heat over 4.5 billion years to continue driving plate tectonics to this day. The moon, being much smaller, lost its internal heat much more quickly. Its mantle cooled and stiffened. The convection that had driven its early volcanic activity, the eruptions that flooded the Maria with lava between 3 and 4 billion years ago, slowed and then largely ceased. The moon's surface, once active, became fixed in something close to its current state. Since then, it has been modified primarily by impacts, the steady rain of meteorites that has continued to reshape the surface without fundamentally renewing it, leaving behind the accumulated cratering record that makes the moon look the way it does through a telescope on a clear night. Walk on the moon and you would not walk on bare rock. You would walk on something soft and powdery and strange, a layer of pulverized material called regolith that covers the entire lunar surface to depths ranging from a few meters at younger sites to tens of meters at older, more heavily bombarded ones. The moon's surface is covered in a layer of pulverized rock called regolith, a fine, powdery soil created by billions of years of meteorite impacts in the absence of wind or water to erode it in any other way. On Earth, the processes that break down rock at the surface are dominated by water and wind, the chemical weathering that dissolves minerals and the physical weathering that chips and grinds rock through the action of moving water, ice expansion, and air-blown particles. These processes are constantly at work on Earth's surface, constantly breaking down rock and transporting the fragments, gradually building the complex layered soils that support terrestrial life in all its diversity. The moon has none of these processes available to it. It has no liquid water, no atmosphere to carry wind, no ice to expand in cracks and shatter rock, no roots pushing through stone. The only process that breaks down rock on the moon's surface is impact, the constant arrival of meteorites large and small, each one shattering rock and mixing the fragments, gradually reducing the surface to finer and finer particles over billions of years of geological time. The regolith that results is unlike any soil on Earth, angular fragments of rock and mineral, glass beads formed by the heat of impacts, and an ultrafine powder that clings to everything it touches, all mixed together into the strange and grey and powdery surface that Armstrong and Aldrin first described stepping into on the Sea of Tranquility. One of the most visually familiar facts about the moon, so familiar that it is easy to forget it is a fact requiring explanation at all, is that we always see the same face. No matter where you are on Earth, no matter what time of year, no matter how many thousands of nights you have spent watching the moon travel across the sky, you always see the same craters, the same dark plains, the same pattern of light and dark that cultures around the world have spent thousands of years finding faces and rabbits and goddesses within. The far side of the moon, the hemisphere that perpetually faces away from Earth, was entirely unknown to human eyes until a Soviet spacecraft photographed it for the first time in 1959, revealing a surface strikingly different from the familiar near side in several important ways. The moon rotates at exactly the same rate that it orbits Earth, a phenomenon called tidal locking, which is why we always see the same face of the moon from Earth. Tidal locking is not a coincidence, and it is not mysterious. It is the inevitable outcome of a physical process that has been operating continuously since the moon's formation. The tidal forces that the Earth exerts on the moon have, over billions of years, gradually slowed the moon's original rotation until it's synchronized exactly with its orbital period. Once that synchronization is achieved, the gravitational geometry of the system maintains it. Any slight departure from synchronization generates a restoring tidal force that brings the moon back into the locked state. The Earth is experiencing the early stages of this same process. In the far future, billions of years hence, Earth too may be tidally locked to the moon, each showing the same face to the other, forever. There is something quietly extraordinary about the idea that the ground beneath your feet, the rock and soil and deep interior of the planet you have spent your entire life living on, contains within it the atoms of a world that no longer exists, not as a trace, not as a contamination, but as a fundamental component woven into the structure of Earth itself. Because most of Theia's iron core merged with Earth's core during the impact, a portion of every iron atom in Earth's deep interior may once have been part of Theia. Iron is the dominant element of Earth's core. The outer core, a liquid shell of molten iron surrounding the solid inner core, is what generates Earth's magnetic field through the motion of electrically conducting liquid metal in patterns driven by the planet's rotation and the temperature differences between the core's inner and outer boundaries. Every piece of iron in that churning, dynamic system participated in the history of the solar system's early chaos. Some of it was always part of Earth, accumulated during the original process of planetary formation from the proto-planetary disk. Some of it arrived with smaller impactors during the early bombardment of the inner solar system, and some of it, a fraction whose precise proportion is still debated by planetary scientists, was delivered by Theia in the final and most dramatic accretion event of Earth's formative history. To think of the Earth's deep interior as containing, somewhere within it, the iron heart of a vanished world, a world that was born, grew, moved through the early solar system for millions of years, and then ceased to exist as an independent entity 4.5 billion years ago, is to feel, just for a moment, the true depth and antiquity of what the planet beneath you is made of and where it came from. The size of Earth's iron core relative to the total size of the planet is not what you would necessarily predict if you modelled Earth's formation without accounting for any major contributions from outside bodies. Earth's core is notably large. It accounts for approximately 30% of Earth's total mass and extends from the centre of the planet to a depth of about 2,900 kilometres. And this size is somewhat anomalous when compared to what simple models of planetary accretion from the original proto-planetary disk would predict for a planet of Earth's overall mass. Earth's unusually large core, larger than would be predicted for a planet of its size by solar system averages, may partly be explained by the addition of Theia's core material during the giant impact. When Theia's iron-rich core merged with Earth's core at the time of the collision, it added to the total iron inventory of Earth's interior in a way that a purely gradual, undisturbed accretion process would not have provided. This additional iron, incorporated into the growing Earth in a single catastrophic event rather than delivered gradually over hundreds of millions of years, may account for part of the discrepancy between what models predict and what we observe. The precise fraction of Earth's core that originated in Theia is not currently known with certainty. It depends on details of the impact dynamics that remain uncertain, but the possibility that the size of our planet's metallic heart was determined in part by the merger with another world's metallic heart is one of the more striking implications of the giant impact hypothesis. Earth is not simply the planet it would have been without Theia. In its deepest interior, it carries the weight of that encounter still. Among all the consequences of the giant impact, perhaps the most quietly profound concerns something that most of us experience without ever thinking about it: the fact that we live on the surface of a planet that is habitable at all. Earth's strong magnetic field, generated by the movement of liquid iron in its outer core, is what stands between the surface of the Earth and the full, unshielded force of the solar wind. Without the magnetic field, the solar wind, the constant stream of charged particles flowing outward from the Sun at hundreds of kilometers per second, would over time strip away Earth's atmosphere as it has stripped away much of Mars's atmosphere over the planet's long history, leaving Mars thin-aired and inhospitable. Without an atmosphere of sufficient density, Earth's oceans would gradually evaporate into space. Without oceans, the chemistry of life as we know it would not be possible. The magnetic field is, in a very direct and traceable sense, one of the essential preconditions for the existence of everything that lives on this planet. Earth's strong magnetic field is generated by the movement of liquid iron in its outer core, and Theia's contribution to that core may have played a role in giving Earth the magnetic shield that has protected life throughout its long history. If the addition of Theia's iron enlarged Earth's core beyond what it would otherwise have been, and if that larger core generates a stronger and more stable magnetic field than a smaller core would, then Theia's legacy includes not just the Moon but the invisible envelope that has kept Earth habitable for billions of years. The shield that keeps us safe may be, in part, the enduring gift of a world that gave itself completely. Science occasionally produces discoveries so unexpected, so strange in their implications, that they require a period of quiet adjustment before their full significance can be absorbed. One such discovery concerns two vast, continent-sized structures hidden deep within Earth's interior. Structures whose nature and origin have become one of the most actively debated questions in modern geology and planetary science. Scientists have found compelling evidence of something strange sitting deep within Earth's mantle. Two continent-sized regions of anomalous rock called Large Low Shear Velocity Provinces, or LLSVPs, that behave differently from the mantle surrounding them. The name is technical and unwieldy, but the phenomenon it describes is genuinely remarkable. Seismic waves, the vibrations that travel through Earth's interior after earthquakes and that scientists use to map the planet's internal structure, move more slowly when they pass through these two regions than when they pass through the surrounding mantle material. This difference in wave speed indicates that the material in these regions is different, chemically distinct, physically different in some way that causes it to interact differently with seismic energy than the ordinary mantle rock around it. The two LLSVPs are enormous. They sit at the very base of Earth's mantle, just above the core mantle boundary, roughly 2,900 kilometers below the surface. Each one is larger in area than a continent. Together, they contain a significant fraction of the total volume of Earth's lower mantle, and they have been sitting there in the deepest interior of the planet for an unknown length of time, unmixed, unassimilated, and deeply mysterious. The discovery of the LLSVPs raised an immediate and fascinating question. What are they made of, and where did they come from? The answer, proposed by a landmark 2023 scientific study published in the journal Nature, is one of the most audacious and intellectually compelling ideas to emerge from planetary science in recent years. A leading new theory suggests these two vast structures, one sitting beneath Africa and one sitting beneath the Pacific Ocean, may be remnants of Theia's ancient mantle material, preserved undisturbed at the base of Earth's mantle for 4.5 billion years since the day of the giant impact. The argument runs as follows. When Theia struck the early Earth, most of its rocky mantle was ejected into orbit and eventually became the Moon. But some fraction of Theia's mantle material, denser than Earth's own mantle, different in its chemical composition, may have sunk into the lower mantle rather than being ejected outward into space. There, at the very base of the mantle, where the density contrast between the mantle and the iron core creates a gravitational boundary that nothing denser than the surrounding mantle can easily cross, Theia's denser mantle material could have settled and remained, too dense to be efficiently mixed into the surrounding mantle by convection, too chemically distinct to be dissolved into the surrounding rock over any timescale thus far elapsed. If this is correct, the two blobs of anomalous material detected by seismologists at the base of Earth's mantle are pieces of Theia, sitting undisturbed since the day the collision happened, the oldest preserved material inside the Earth, ancient beyond any other geological context we have words for. The hypothesis that the LLSVPs are remnants of Theia's mantle is intellectually thrilling, but science proceeds most reliably not by choosing the most exciting explanation available, but by carefully evaluating all competing explanations against the full body of available evidence. And there is a competing explanation for the LLSVPs that deserves serious and equal consideration, one that many geophysicists find equally or more persuasive than the Theia hypothesis. Other scientists offer a different explanation for these vast structures, that they are simply ancient slabs of Earth's own oceanic crust, subducted over billions of years and accumulated at the mantle's base. The true origin of these structures remains one of geology's great open questions. The process of subduction, in which dense oceanic crustal plates sink beneath lighter continental plates at convergent boundaries and descend slowly into the mantle, has been operating on Earth for billions of years. As subducted oceanic crust descends through the mantle, it carries with it the chemical and mineralogical signature of ocean floor rock, which is compositionally different from the deeper mantle it sinks into. Some models of subduction dynamics predict that subducted slabs could accumulate at the core mantle boundary, piling up over billions of years into reservoirs of ancient oceanic crust that would be denser and chemically distinct from the surrounding mantle, in ways that could produce exactly the seismic anomalies observed in the LLSVPs. Both hypotheses make predictions that current data cannot yet definitively distinguish between. The question remains open. The debate is ongoing, and the answer, when it eventually comes, will tell us something profound about the deep interior and the most ancient history of this planet. Whatever the ultimate origin of the LLSVPs turns out to be, whether they are pieces of Theia preserved for 4.5 billion years or accumulated slabs of ancient subducted oceanic crust piled up over geological time, their influence on the Earth above them is real, measurable, and ongoing. The LLSVPs influence Earth's deep interior dynamics and may play a role in the location of volcanic hotspots on the surface today, including those that feed the volcanoes of Hawaii and Iceland. Volcanic hotspots are regions of anomalously high volcanic activity that persist in roughly the same geographic location for tens of millions of years, independent of the movement of the tectonic plates above them. Unlike the volcanoes that form at the boundaries between tectonic plates, where the dynamics of plate collision or separation directly drive volcanic eruptions, hotspot volcanoes appear to be fed by plumes of hot material rising from the deep mantle, perhaps all the way from the core mantle boundary. The Hawaiian island chain stretching across the Pacific Ocean in a line that records the steady movement of the Pacific plate over a fixed, deep heat source was formed by the plate slowly drifting over one such hotspot, with successive islands building up as the plate carried earlier volcanic islands away from the source and new ones formed in their place. The edges of the LLSVPS, the boundaries between these anomalous structures and the surrounding mantle, appear to be preferential locations for the initiation of these deep mantle plumes. Whether the LLSVPs are made of ancient Theia or ancient subducted rock, they are shaping the volcanic geography of the surface world above them, connecting the deep past to the actively erupting present. Water is so fundamental to life on Earth that it is easy to take it for granted, to treat the oceans as simply the background against which the story of life has unfolded, rather than as a substance that had to be delivered to this planet through specific processes in the early solar system, processes that are still not fully understood. The origin of Earth's water is a question that planetary scientists have been working on for decades, and while much of the answer involves comets and water-bearing asteroids from the outer solar system, the role of the giant impact in the story of Earth's water budget is an interesting and still actively debated one. Theia's water and volatile compounds, if it carried any, may have contributed to early Earth's inventory of materials that eventually gave rise to the oceans. Whether Theia was water-rich or water-poor depends on where in the solar system it formed and what the specific conditions were in that region of the protoplanetary disk during the period of its formation. If Theia formed in the inner solar system, it was likely not particularly water-rich. The inner solar system is generally too warm for water ice to condense easily, and rocky bodies there tend to have limited volatile inventories compared to their outer solar system counterparts. But if Theia had accreted some water-bearing minerals during its formation, hydrated silicates which can carry water chemically bound within their crystal structures, then the impact may have delivered some fraction of that water to the Earth-Moon system. Some was lost in the heat of the impact, some may have been incorporated into the Moon itself, and some may have remained in the Earth, adding its small contribution to the water budget that eventually filled the earliest oceans. Beyond water, the role of Theia as a possible delivery vehicle for some of the chemical building blocks of life represents one of the more speculative but genuinely fascinating threads in the broader story of how Earth became a habitable and life-bearing world. The impact with Theia may have also delivered additional carbon and nitrogen to Earth, elements essential to life, if Theia had accreted these materials from the outer solar system before the collision. Carbon and nitrogen are among the most important elements in all of biochemistry. Carbon forms the backbone of all organic molecules, the proteins, the nucleic acids, the lipids and carbohydrates that make up every living cell on Earth. Nitrogen is an essential component of amino acids, which are the building blocks of proteins and of the nucleotide bases that encode genetic information in DNA and RNA. Without both of these elements in adequate supply at the right place and time, life as we know it could not exist. The early Earth's inventory of carbon and nitrogen, where it came from, how it was acquired, what form it was in during the critical early period when life first arose, is a question that remains at the active frontier of planetary science research. Some models suggest that much of Earth's carbon and nitrogen was delivered by impactors from the outer solar system, where these elements are more abundant than in inner solar system rocky bodies. If Theia, in the course of its millions of years of existence before the collision, had acquired any material from outer solar system sources, then the giant impact may have delivered some of those ingredients, adding one more remarkable thread to Theia's already extraordinary contribution to the planet we inhabit and the life that covers it. The relationship between the giant impact and the origin of life on Earth is one of the more philosophically interesting questions that the Theia hypothesis opens up, a question that sits at the intersection of planetary science, chemistry, and the deepest uncertainties about how living systems first arose on any world. Some scientists believe Theia's impact may have fundamentally reset early Earth's chemical evolution, destroying whatever pre-existing chemistry had accumulated and restarting the conditions for life from a new beginning. Before the giant impact, Earth had been accumulating material and developing its chemistry for tens of millions of years. Whether any of that pre-existing chemistry was interesting from the perspective of the origin of life, whether any of it represented the beginning of prebiotic chemistry, the first tentative molecular steps toward the kind of self-organization that would eventually lead to the first living cell, is unknown and perhaps unknowable. The giant impact destroyed whatever had accumulated. the global magma ocean erased the surface chemistry completely. The loss of the early atmosphere reset the volatile inventory. Whatever had been building on the pre-impact Earth was entirely wiped clean. In this sense, the giant impact was a reset, a catastrophic interruption of whatever process had been underway, a return to the most basic initial conditions of a newly formed rocky world. But it was also, in the same event, a resetting that provided entirely new conditions. A new atmosphere eventually built up, new oceans formed, a moon now existed to drive tides and stabilize the tilt, a magnetic field perhaps strengthened by Theia's iron. The giant impact ended one story and started another, and the story it started eventually led to you. The question of whether life existed on Earth before the giant impact, and whether it could have survived such a collision, touches on some of the most profound uncertainties in the study of life's origin and the conditions it requires. The heat from the giant impact would have sterilized Earth completely, meaning that if any primitive life had somehow emerged before the impact, it would not have survived what came after. This conclusion follows directly and inevitably from the physics of the event. The global magma ocean that covered Earth in the aftermath of the impact reached temperatures sufficient to melt rock, well above any temperature at which any known biochemistry can function. Even the most heat-tolerant organisms known on Earth today, the hyperthermophilic archaea that live in deep-sea hydrothermal vents and hot springs, thriving at temperatures close to the boiling point of water, would have been instantly and completely destroyed in the environment of the post-impact Earth. There was nowhere to shelter. The heat was not localized to any particular region. It was global, total, and sustained for thousands of years. Any molecule that had achieved the complexity of a living system, had it somehow existed before the impact, would have been broken down into its constituent atoms by the sustained heat of the magma ocean that followed. The chemistry of life would have had to begin again from the simplest possible molecular precursors, in an environment that was slowly, painfully patient, recovering from the most violent event in Earth's history. Whether life began before the giant impact, only to be erased and forced to start again, is one of the great unanswerable questions at the edge of everything we know. To truly understand the world that existed in the immediate aftermath of the giant impact is to understand that almost nothing about it resembled the Earth we know. Not its surface, not its atmosphere, not its temperature, not its day length, not any feature we would recognize as belonging to the world we inhabit. The post-impact Earth, covered in magma, spinning rapidly, wrapped in a thick steam atmosphere, was a radically different world than the one that had existed before Theia arrived, and a radically different world than the one that exists today. The global magma ocean that covered the surface to depths of hundreds of kilometers gave the planet a surface that glowed, visible from space as a luminous body, radiating heat at wavelengths corresponding to temperatures of thousands of degrees. Above this glowing surface rose an atmosphere unlike anything Earth has had since, composed primarily of water vapor and carbon dioxide, and the mineral vapors cooked out of the magma below, so thick and so hot that it acted as a thermal blanket, slowing the rate at which the surface could radiate its heat away into space and extending the duration of the magma ocean phase by thousands of years. The planet was spinning fast, so fast that the day-night cycle, if you could call it that, on a world with no solid surface was a matter of only a few hours. The newly forming moon loomed enormous in the sky above, close enough that its tidal influence on the magma ocean was profound and continuous, raising waves in liquid rock, adding frictional heat, shaping the interior of the world it had helped create. The transition from the post-impact magma world to the water-covered planet that eventually gave rise to life required patience, the patient, unhurried patience of deep time, of a planet cooling degree by degree, century by century, across hundreds of millions of years of gradual and continuous change. The gradual cooling of the post-impact Earth over hundreds of millions of years eventually allowed the steam atmosphere to condense into liquid water, forming the earliest oceans. The thick steam atmosphere that blanketed the post-impact Earth was not a passing feature that dissipated quickly. It was a sustained phenomenon, a thermal blanket so dense that it effectively trapped the heat of the magma ocean, slowing the cooling process and extending the life of the molten surface long beyond what a thinner atmosphere would have allowed. For as long as the surface remained hot enough to vaporize water, all water in the Earth-Moon system existed as vapor in the atmosphere rather than as liquid anywhere on the surface. Only when the surface finally cooled below a critical threshold, when the energy balance tipped from the magma ocean maintaining temperatures above water's boiling point to the atmosphere cooling enough to allow liquid water to persist at the surface, did the conditions exist for sustained rainfall. And when that threshold was crossed, the rain that fell was not the gentle rain of a settled and hospitable world. It was a sustained global deluge of hot water, falling from a thick steam atmosphere onto a surface that was still cooling, still releasing heat from the deep interior, still far from anything we would recognize as land or sea or shore. The first oceans formed this way, slowly filling the low-lying basins of a cooling world, one raindrop among billions, century after patient century. The giant impact hypothesis, the theoretical framework that places Theia at the center of the moon's origin story, is not an ancient idea passed down through generations of scientific tradition. It is a remarkably recent one, developed within the last 50 years, refined through decades of modeling and observation and debate, and still actively extended and challenged today. The giant impact hypothesis was first formally proposed in 1974 by William Hartmann and Donald Davis, and independently by Alistair Cameron and William Ward in 1976. The fact that it was proposed independently by two different research teams within a few years of each other is itself significant. It suggests that the hypothesis arose not from a single flash of individual insight but from a convergence of scientific thinking, as multiple researchers engaging with the same body of data and the same theoretical frameworks arrived independently at the same general conclusion. Hartmann and Davis, working from considerations of the dynamics of planetary accretion in the early solar system, proposed that the moon could have formed from debris ejected by a giant impact on the early Earth. Cameron and Ward approached the problem from a different angle entirely, focusing on the angular momentum of the Earth-Moon system, the total rotation and orbital motion of the two bodies, and concluding that the only way to account for that angular momentum was through exactly the kind of oblique giant impact that Hartmann and Davis had independently described. Both pairs of researchers were working in the aftermath of the Apollo missions, with access to the first detailed chemical and isotopic analyses of lunar samples, and those samples were providing data that the existing theories of lunar origin could not adequately explain. The giant impact hypothesis did not emerge into a scientific vacuum. It was proposed as an alternative to three earlier theories for the moon's origin, each of which had its own genuine strengths and its own critical weaknesses, and none of which could fully account for all of the moon's observed properties simultaneously. Before the giant impact hypothesis, scientists proposed three other main theories for the moon's origin: co-formation, fission, and capture, each of which failed to fully explain the moon's composition and orbital characteristics. The co-formation hypothesis proposed that the Earth and Moon formed together from the same cloud of material in the early solar system, as a kind of binary planet system growing side by side from the same disk material. This hypothesis could explain the chemical similarity between Earth and Moon rocks, but it struggled to explain the Moon's low density and small iron core. If both formed from the same material and the same process, they should have similar iron contents, and they do not. The fission hypothesis, most associated with the 19th century astronomer George Darwin, proposed that the early Earth was spinning so fast that it became rotationally unstable and flung off a portion of its outer layers, which then formed the Moon. This hypothesis naturally explains the Moon's chemical similarity to Earth's outer layers, but it requires an initial spin rate for Earth that is difficult to achieve through any known mechanism. The capture hypothesis proposed that the Moon formed elsewhere in the solar system and was gravitationally captured by Earth during a close approach. But gravitational capture without significant energy dissipation is dynamically very unlikely, and capture from a different region of the solar system would likely produce a moon with a different chemical signature from Earth's mantle. Only the giant impact hypothesis addresses all constraints simultaneously. There are moments in the history of science when a collection of physical objects, rocks, fossils, particles, spectra, becomes more than the sum of its parts and changes the trajectory of an entire scientific field. The Apollo lunar sample collection is one of those moments, one of those collections. The Apollo missions, running from 1969 to 1972, returned approximately 382 kilograms of moon rocks to Earth, and the detailed chemical analysis of those samples became the foundation upon which the giant impact hypothesis was built and refined. 382 kilograms is not a large quantity by the standards of geological fieldwork on Earth. A geologist studying the rocks of a mountain range might carry more than that in a single season. But every gram of those Apollo samples was irreplaceable, collected at enormous effort and cost and risk from 6 different sites on the Moon's surface, representing the first direct physical connection between Earth's scientific community and another world. The detailed chemical and isotopic analyses of those samples revealed things that no telescope observation could ever have shown. The specific mineral assemblages of the lunar highlands, the composition of the mare basalts, the oxygen isotope ratios that matched so closely to Earth's own signature, the pattern of volatile element depletion that pointed toward an extremely hot formation environment. Each new measurement was a constraint, a property of the Moon that any successful theory of its formation would have to explain. And the constraints, taken together, pointed with increasing clarity toward exactly the kind of formation scenario that the giant impact hypothesis described. The rocks of the Moon told the story of Theia before anyone had a name for it. Among all the chemical properties of the Moon that must be explained by any successful theory of its origin, the depletion in volatile elements stands out as one of the most diagnostically important, and one of the most naturally and elegantly explained by the giant impact hypothesis. One of the most compelling pieces of evidence for the giant impact hypothesis is the Moon's depletion in volatile elements, substances like water, sodium, and potassium that evaporate at high temperatures, consistent with forming from an extremely hot debris disk. Volatile elements are those that have relatively low boiling points, substances that convert from solid or liquid to gas at temperatures well below those achieved at planetary interiors, but that would be readily and completely vaporized in the extreme heat of a giant impact debris disk. On Earth, volatiles are present in considerable quantities. Water fills the oceans and saturates the crust. Sodium and potassium are abundant in the crust and mantle and seawater, and many other volatile elements are distributed throughout Earth's geological systems in significant amounts. On the Moon, these same elements are dramatically and systematically depleted. The Moon is, by the standards of planetary chemistry, almost entirely desiccated. It formed in conditions so ferociously hot that the volatile elements could not efficiently be retained, evaporating away from the forming Moon and escaping into space from the debris disk before they could be incorporated into the growing satellite. This depletion is exactly what you would expect if the Moon formed from an extremely hot debris disk generated by a giant impact, and it was one of the earliest and most powerful lines of evidence that the Apollo samples provided in support of that hypothesis. The scientific consensus that has formed around the giant impact hypothesis over the past 50 years is a reflection not of mere fashion or institutional momentum, but of the hypothesis's remarkable ability to simultaneously explain a wide variety of independent observational constraints that no competing theory could address with equal success. The giant impact hypothesis is now the dominant scientific model for the Moon's formation and is accepted by the overwhelming majority of planetary scientists. This acceptance is not unconditional or uncritical. Science does not operate through unconditional acceptance of any theory, and the giant impact hypothesis continues to be tested, refined, and challenged by new data, new modeling capabilities, and new theoretical frameworks as they become available. But the core claim, that the Moon formed from debris generated by the collision of a Mars-sized body with the early Earth approximately 4.5 billion years ago, is supported by enough independent lines of evidence that the scientific community has reached a strong and well-grounded consensus in its favor. The Moon's mass, orbital characteristics, and angular momentum relationship with Earth are all consistent with it. The Moon's depletion in volatile elements is consistent with it. The Moon's small iron core is consistent with it. The compositional similarity of Moon rocks to Earth's mantle is consistent with it. The oxygen isotope data is consistent with it. No other proposed mechanism for the Moon's formation can explain all of these properties simultaneously. The giant impact hypothesis can. That convergence of explanatory power, the ability of a single hypothesis to account for multiple independent lines of evidence, is one of the strongest signals available in science that a theory is pointing towards something real. The tools that scientists use to study the giant impact have evolved dramatically over the decades since the hypothesis was first proposed in the 1970s. In those early years, working out the consequences of a planetary-scale collision was a task that required simplified analytical models and a great deal of physical intuition, because the computational power needed to realistically simulate the actual physics of such an event simply did not yet exist in any accessible form. Today, the situation is entirely different. Modern simulations of the giant impact use supercomputers running physics models that track millions of particles of simulated rock and metal, allowing scientists to test different impact angles, speeds, and sizes to see which scenario best reproduces the moon we actually observe. These simulations, called smoothed particle hydrodynamics simulations or SPH simulations, represent each body as a collection of individual particles, each particle carrying properties like mass, velocity, temperature, and material type, and solve the equations of fluid dynamics and gravity to determine how each particle moves and interacts with all the others across the duration of the collision and its immediate aftermath. A modern simulation of a giant impact scale event might track millions of particles across a simulation time of several hours to days of modeled physical time, the computational equivalent of watching an entire planet be destroyed in slow motion, particle by particle, consequence by consequence. The results of these simulations can be compared directly to the observed properties of the Moon and Earth, their masses, their compositions, their orbital characteristics, and the impact parameters that best reproduce the observations can be progressively identified and refined. Science is not static, and the giant impact hypothesis, for all the consensus it has attracted and maintained over several decades, continues to evolve as new data, new modeling capabilities, and new theoretical frameworks bring fresh perspectives to questions that were thought to be settled. Variations in the giant impact hypothesis continue to be refined. Some models suggest the impact may have been more head-on than originally thought, or that Theia may have been larger or smaller than a Mars-sized body. The original formulation of the hypothesis, as proposed in the 1970s, described an oblique impact by a Mars-sized body as the best fit to the observed properties of the Earth-Moon system. But as simulations became more sophisticated and as observational constraints were added and refined, particularly the extremely tight isotopic similarity between Earth and Moon rocks, which turned out to be even more precise than initially measured, some researchers found that the original scenario did not fully reproduce all of the observations. Specifically, the original scenario tended to produce a moon whose composition reflected predominantly Theia's mantle rather than Earth's mantle, but the isotopic similarity of Earth and Moon rocks suggested that both bodies' material was very thoroughly mixed in the formation process. This observation prompted the exploration of alternative scenarios: a more energetic and more head-on impact, a smaller and faster Theia, a larger and slower one, different initial conditions for Earth's rotation. Each variant produces somewhat different outcomes for the debris disk and the Moon's eventual composition. The search for the variant that best reproduces all observations simultaneously is ongoing, a scientific conversation that has been running for 50 years and shows no signs of reaching its final conclusion. One of the most imaginative and scientifically productive developments in the continuing refinement of the giant impact hypothesis is a variant that reimagines not just the details of the impact, but the fundamental nature of the post-impact Earth itself, replacing the conventional image of a planet surrounded by a debris disk with something far stranger, far more extreme, and far more difficult to picture. One compelling variation proposed in 2012 suggests the impact may have been so energetic that Earth was briefly transformed into a rapidly rotating donut-shaped cloud of vaporized rock, a structure scientists call a Synestia, with the Moon condensing from within this structure rather than from a traditional debris disk surrounding an otherwise recognizable planet. The Synestia model takes its name from the Greek word for together combined with the Latin word for structure, a coining that describes a body that is neither a planet nor a disk but something in between, and something with no ordinary counterpart in the solar system as it exists today. A synestia forms when two planetary bodies collide with enough energy and enough angular momentum that the resulting merged object contains more angular momentum than any solid planet can carry, more than the maximum spin rate of any solid body. At that point, the excess angular momentum causes the body to expand dramatically outward, puffing into a bloated, donut-like structure of vaporized rock in which the distinction between planet and surrounding disk is erased, replaced by a single, continuous, rapidly rotating body of mineral vapor within which the Moon could condense not from outside but from within. The Synestia model addresses one of the most persistent and important challenges facing the classical version of the giant impact hypothesis, a challenge that planetary scientists sometimes call the isotopic crisis, and that concerns the extraordinary degree of chemical similarity between Earth and Moon rocks. The Synestia model is a fascinating and still debated proposal that offers a potential explanation for one of the giant impact's deepest mysteries: why Earth and Moon rocks are so chemically identical, a mystery that the Synestia model resolves by having both form from within the same thoroughly mixed body of vaporized material. The problem is this. In the classical giant impact scenario, the Moon forms primarily from material derived from Theia's mantle, the material that is ejected into orbit during the oblique impact. Earth's own mantle material contributes less to the Moon. The result should be a Moon whose composition reflects predominantly Theia's mantle rather than Earth's mantle. But the isotopic data from the Apollo samples suggests that the Moon looks almost identical to Earth's own mantle composition. In the Synestia model, this problem is resolved naturally and elegantly. If the impact is energetic enough to create a Synestia, a single, thoroughly mixed body of vaporized rock in which both Theia's material and Earth's material are uniformly blended together, then any solid body that condenses from within that Synestia will have the same isotopic composition as the Synestia as a whole. The Moon condensing from inside the Synestia would inherit that uniform blend, and would be isotopically indistinguishable from the Earth that emerged from the same vaporized, well-mixed structure. For all its elegance as a solution to the isotopic challenge, the Synestia model is not without its own uncertainties and complications, and it has not yet displaced the classical debris disk version of the giant impact hypothesis as the standard framework cited in planetary science courses and introductory textbooks around the world. While the Synestia model has not yet replaced the classical debris disk model as the standard explanation, it represents one of the most thought-provoking new ways scientists are reconsidering what the moments after the giant impact may truly have looked like, and what processes within that extreme environment gave rise to the Moon we observe. The Synestia model requires a more energetic impact than the classical scenario, higher impact velocity, more total angular momentum. And while some specific impact scenarios can produce a Synestia, not all can, and the constraints that would determine whether the actual giant impact produced one are not yet precisely enough known to settle the question definitively. It also requires that the Synestia remain sufficiently hot and well mixed for long enough that the Moon can condense from within it before the Synestia cools and collapses back into a more recognizable planet plus disk configuration. The details of how and where within the Synestia the Moon condenses and how its final composition is determined by the cooling and condensation process inside such a structure are still being actively worked out. What the Synestia model represents, in the broader scientific conversation, is not a replacement of the giant impact hypothesis, but a deepening of it, an attempt to push beyond the broad strokes picture into a more detailed and more physically complete understanding of what actually happened. The story of the giant impact is told in the rocks of the Moon, but it is also told more faintly and more indirectly in the rocks of Earth itself, and scientists continue to search those rocks for signatures that might further constrain what happened and when. Scientists continue to search for additional evidence of the giant impact in the geological record of both Earth and the Moon, including in the isotopic compositions of various elements and in the structure of Earth's deep interior. On the Moon, the search is relatively straightforward in principle. The Moon's geological history is simpler than Earth's. Its surface has not been recycled by plate tectonics, and the oldest rocks are still accessible at the surface, albeit heavily pulverized by billions of years of meteorite impacts. The lunar highlands provide the oldest accessible material, and their age and composition continue to be refined as new analytical techniques are applied to existing Apollo samples, and as scientists plan and advocate for future missions that might return samples from previously unsampled regions of the lunar surface. On Earth, the search is considerably more difficult. Earth's geological record has been so thoroughly mixed and recycled by plate tectonics, erosion, and volcanic activity that any material dating back to the time of the giant impact, 4.5 billion years ago, would be extraordinarily rare at the surface. The oldest known mineral grains on Earth are zircons from Western Australia, some of which date to approximately 4.4 billion years ago, tantalizingly close to the time of the giant impact, and their chemistry provides some constraints on the conditions of early Earth that are still being carefully interpreted. There is something deeply fitting about the fact that the story of Theia, a world that existed for tens of millions of years and was destroyed 4.5 billion years ago, continues to generate new scientific research, new hypotheses, and new discoveries in the 21st century. Despite being 4.5 billion years old, the story of Theia continues to generate new research, and new findings continue to add unexpected layers to one of science's most ancient and most consequential mysteries. The giant impact hypothesis has been the dominant theory of lunar origin for roughly 4 decades, but it has not settled into the static certainty that marks a fully solved and finished problem. New observational data from lunar samples, including reanalysis of existing Apollo samples with techniques that did not exist when they were first collected, continues to refine the isotopic picture and provide new constraints for theoretical models. New simulations, enabled by ever-increasing computational power and ever-improving physics models, explore parameter spaces that earlier models could not reach. New theoretical frameworks like the Synestia model open up possibilities that had not been seriously considered in the early years of the hypothesis. And new discoveries, like the LLSVP findings and their possible connection to Theia's mantle published in 2023, suggest that Theia's legacy may be more extensive and more directly preserved inside the Earth than anyone had imagined. Science works this way, not in straight lines from ignorance to certainty, but in spirals, returning again and again to the same questions with better tools, more data, and more sophisticated frameworks. The story of Theia is one of those questions. The spiral continues. The moon is leaving, not quickly, not in any way that registers on the timescale of a human lifetime, or a dozen human lifetimes, or 1,000. But the moon is, measurably and continuously, year by year, moving away from the Earth. And the reason it is doing so is the same gravitational relationship that has connected it to Earth since the first days of its formation from the debris of the giant impact. The moon is slowly moving away from Earth at a rate of approximately 3.8 centimeters per year, a consequence of tidal interactions between the two bodies that have been operating continuously for 4.5 billion years. 3.8 centimeters is a small distance. It is roughly the width of 2 adult fingers placed side by side. In the context of the 384,000 kilometers that currently separate Earth and Moon, it is an almost imperceptible change. A fraction of the total distance, impossible to detect with anything other than the most precise instruments ever built. Astronomers know this rate because of laser ranging experiments in which laser pulses are bounced off retroreflector arrays left on the moon's surface by Apollo astronauts, and the round-trip travel time is measured with extraordinary precision, allowing the distance to be calculated to within millimeters. The mechanism is tidal. Earth's rotation carries the tidal bulge that the moon raises in Earth's oceans slightly ahead of the point directly beneath the moon, and the gravitational attraction between the moon and this slightly forward-displaced bulge accelerates the moon in its orbit, which causes it to spiral slowly outward. Energy is transferred from Earth's rotation to the moon's orbit. Earth slows, the moon moves away, and the process has been running uninterrupted for billions of years. To understand how profoundly the moon's appearance in Earth's sky has changed since the moment of its formation is to understand something important about the relationship between distance and apparent size, and about how utterly different the sky above the early Earth would have appeared from the sky you see on any night you choose to look up. When the moon first formed, it was so close to Earth that it appeared roughly 15 times larger in the sky than it does today. 15 times larger in apparent angular diameter means not just a slightly bigger moon, but an almost unrecognizably transformed sky. The moon as we see it tonight occupies about half a degree of arc in the sky, roughly the same apparent size as the sun, which is why total solar eclipses are possible, the moon's disk exactly covering the sun's. A moon 15 times larger in apparent diameter would cover more than 7 degrees of arc, an enormous, looming presence that would have dominated the sky in a way that has no parallel in any human being's experience of looking upward at the night sky. It would have been clearly visible in broad daylight, even before it reached full phase. Its reflected light on a clear night would have been dramatically brighter than the brightest full moon we know today. The tidal forces it exerted on the still-forming Earth at that distance would have been orders of magnitude more powerful than the gentle tides we experience today in even the most tide-sensitive coastlines on Earth. The sky of the early Earth, in the first millions of years after the Moon's formation, was a sky dominated by a vast glowing companion, closer and larger and more gravitationally present than anything in the experience of any creature that has ever lived on this planet. The rhythmic rise and fall of the ocean, the tides that mark every coastline on Earth with their eternal coming and going, that have shaped the margins of continents for billions of years, that have provided the ecological niches in which some of the most adaptively extraordinary organisms on Earth have evolved, are at their heart a consequence of Theia. The Moon's gravitational pull is the primary driver of Earth's ocean tides, the rhythmic rise and fall of sea levels that has shaped coastlines, marine ecosystems, and the conditions for early life for billions of years. The mechanism of tidal generation is the differential gravitational attraction of the Moon across the diameter of the Earth. The side of Earth closest to the Moon experiences a slightly stronger gravitational pull than the center of the Earth, and the center experiences a slightly stronger pull than the far side. These differences in gravitational force across the Earth's body, the tidal force, cause the oceans to bulge slightly in the direction of the Moon on the near side and, by the geometry of the system, on the far side as well. As the Earth rotates beneath these tidal bulges, different parts of the coast pass through regions of higher and lower water level, producing the rise and fall we call tides. The details vary enormously from place to place. Some coastlines experience barely perceptible tidal ranges, while others, like the Bay of Fundy in eastern Canada, experience tidal ranges of 15 meters or more because of specific resonances in the basin's geometry. But the driving force, everywhere on every coast of every ocean, is the same. The gravity of a body that was itself born from the giant impact, from Theia, from the most consequential event in Earth's formative history. Of all the Moon's influences on the long-term character of Earth as a habitable planet, perhaps none is more invisible in its day-to-day operation and more profound in its long-term consequences than the Moon's role in stabilizing the orientation of Earth's rotational axis. The Moon stabilizes Earth's axial tilt. Without it, Earth's obliquity could vary chaotically between 0 and 85 degrees over millions of years, causing extreme and destabilizing climate swings that might have made the long-term evolution of complex life on this planet very difficult or impossible. The axial tilt of a planet is not inherently stable on its own. In the absence of a large stabilizing influence, the gravitational tugs of the other planets, particularly Jupiter, whose gravitational influence reaches across the entire solar system and affects the orbits of everything in it, would cause the tilt of a planet like Earth to wander over millions of years, driven by gravitational resonances that slowly shift the orientation of the rotational axis in complex, non-periodic, and essentially unpredictable ways. Mars, which has no large moon, experiences exactly this kind of chaotic variation in its axial tilt. Models of Mars's rotational history suggest that its obliquity has ranged from nearly 0 to as much as 60 degrees over the past billion years, producing dramatic climate swings that make Mars's ancient history of potential habitability deeply uncertain. Earth, with its large moon, is protected from this kind of chaos. The Moon's gravitational influence on Earth's equatorial bulge creates a strong and persistent stabilizing torque that resists the wandering of the tilt, keeping it within a relatively narrow range centered around 23.5 degrees across geological time. The Moon's stabilizing effect on Earth's axial tilt is not just a feature of this particular moment in Earth's geological history. It is a condition that has persisted for billions of years, and one that may have been essential for the development of the complex and diverse biological life that characterizes Earth's biosphere today and throughout its long history. The Moon's stabilizing effect on Earth's axial tilt is considered by many scientists to be one of the key factors that has allowed Earth's climate to remain relatively stable across the billions of years needed for complex life to evolve. A stability that may have been essential for the long and cumulative development of biological complexity. Complex life, multicellular organisms, plants, animals, fungi, the extraordinary diversity of forms that covers almost every surface of this planet, took approximately 3 billion years to develop after the first living cells appeared in the early oceans. Those 3 billion years required a planet that was habitable throughout, a planet with persistent liquid oceans, with a carbon cycle capable of regulating atmospheric temperature across geological timescales, with sufficient chemical complexity to support the eventual evolution of photosynthesis and the oxygen-producing organisms that transformed the entire atmosphere. None of that long, cumulative biological work would necessarily have been possible if Earth's axial tilt were varying chaotically by tens of degrees on million-year timescales. Extreme obliquity variations would produce extreme seasonal differences that might have periodically frozen entire ocean basins and then boiled them. Cycles too rapid and too severe for the patient processes of evolution to track and adapt to reliably. The Moon stabilized the tilt. The stable tilt stabilized the climate. The stable climate gave life enough time to become everything that life on Earth has become. The slowing of Earth's rotation by the Moon's tidal forces is one of the most elegantly documented processes in all of Earth science, a phenomenon recorded not just in the precision measurements of modern laser-ranging experiments, but in the geological record of ancient ocean sediments, in the growth rings of fossil corals, and in the banding patterns of ancient tidal flat deposits laid down hundreds of millions of years ago. The Moon has been gradually slowing Earth's rotation through tidal friction. In the earliest days after the giant impact, a day on Earth may have lasted as little as 2 to 5 hours. Today, it lasts 24 hours. In the distant future, a day may stretch to 1,000 hours or more. The evidence for this long-term deceleration is written in rock, literally. Fossil corals from the Devonian period, approximately 380 million years ago, show daily growth rings that indicate the year at that time contained approximately 400 days, meaning Earth was rotating roughly 400 times per year, rather than the 365 times it does today. Ancient tidal rhythmites, layered sedimentary deposits that record the tidal cycles of ancient shallow seas, show tidal patterns consistent with a shorter day and a closer moon going back more than 1 billion years into the geological past. Each line of evidence is independent, but all tell the same story. Earth's day has been lengthening throughout its history, driven by the Moon's tidal breaking. The 24-hour day you live in is not a fixed feature of the solar system. It is a snapshot of an ongoing process, one day in the long, slow deceleration of a planet's spin. The tidal interaction between Earth and the Moon is a two-way relationship, a mutual exchange of energy and momentum that affects both bodies simultaneously, even though the effects on the larger, more massive Earth are less dramatic in any given year than the effects on the smaller Moon. The same tidal forces that slow Earth's rotation are gradually accelerating the Moon in its orbit, which causes it to spiral slowly outward, increasing its distance from Earth over time at the rate of 3.8 centimeters per year. This is the mechanism of the Moon's recession, and it is, in its logic, somewhat counterintuitive. As Earth's rotation slows, the tidal bulge that the Moon raises in Earth's oceans, which is slightly ahead of the sublunar point due to the frictional delay of the water responding to the Moon's pull, exerts a gravitational pull on the Moon in the forward direction of its orbit. This forward pull adds energy to the Moon's orbital motion, which in orbital mechanics causes the Moon to move to a higher, more distant orbit rather than a closer or faster one. It seems counterintuitive that pulling the Moon forward makes it move away rather than inward, but this is the nature of orbital dynamics. Adding energy to an orbit raises its altitude. The transfer of energy from Earth's rotation to the Moon's orbit is a beautifully closed and elegant system. Earth gives up its spin energy, the Moon takes it and moves away, and over 4.5 billion years of this continuous exchange, the Moon has traveled from 20,000 kilometers away to nearly 400,000 kilometers away. The exchange will continue for as long as both bodies exist. The connection between the Moon's tidal forces and the possible origin of life on Earth is one of the more intriguing threads in the scientific study of how living systems first arose on this planet, a thread that connects the physics of orbital mechanics to the chemistry of the earliest biology in a way that is both scientifically grounded and quietly beautiful to contemplate. Earth's tidal systems, driven by the Moon, are thought to have played a role in the origin of life, creating rhythmic cycles of wet and dry conditions in coastal tidal pools where early chemistry could concentrate, interact, and build complexity over time. The hypothesis runs as follows. In the early ocean, the chemical precursors of life, organic molecules, nucleotides, amino acids, lipids, would have been dissolved and distributed through an enormous volume of water. At those concentrations, the probability of any two molecules meeting and reacting in a productive way would have been low enough to seriously impede the formation of more complex molecular structures. Concentration is required, some mechanism that brings the molecules together in a small enough volume that productive interactions can occur with reasonable frequency. Tidal pools provide exactly this mechanism. As the tide rises, ocean water floods coastal pools, bringing with it a fresh supply of dissolved organic molecules. As the tide falls, the water evaporates, concentrating the molecules remaining in the pool. Then the tide rises again, brings new molecules, dilutes the pool slightly, then falls and concentrates again. This rhythmic alternation, driven by the moon's gravitational pull and therefore ultimately by Theia's collision, creates an environment in which molecular concentrations can build toward the thresholds needed for more complex chemistry to occur. The tidal relationship between the early moon and the early Earth did not only operate at the surface, in the oceans that would eventually fill Earth's basins, or in the global magma ocean of the immediate post-impact period, it also reached into the interior of the planet itself, generating heat through the deformation of rock under tidal stress, and contributing in this way to the volcanic and geological activity that helped shape the early Earth's surface and atmosphere. The moon's gravitational influence helped shape early Earth's interior through tidal heating, contributing to volcanic activity that released gases forming the early atmosphere. Tidal heating is a process most familiar from the study of the moons of Jupiter, particularly Io, the innermost large moon of Jupiter, whose orbital resonances with the other Galilean moons subject it to such intense tidal flexing that it is the most volcanically active body in the entire solar system, its surface constantly being renewed by eruptions that result directly from the heat generated by tidal stress. The early Earth, with the moon so much closer than it is today, would have experienced tidal heating of a comparable if less extreme character, the moon's near-field gravity squeezing and relaxing the planet's interior with each orbital period, generating heat through friction within the rock, contributing to the volcanic outgassing that built up the secondary atmosphere that replaced the one stripped away by the giant impact itself. Volcanoes releasing carbon dioxide and water vapor and nitrogen into the early atmosphere were doing so in a world that was being tidally squeezed by the moon, a moon that itself existed only because of Theia's ending. There is a quiet melancholy in contemplating the future of the moon's relationship with Earth, a future in which the moon will gradually become too distant, too small in the sky for one of the most beautiful astronomical phenomena visible from anywhere on Earth's surface to continue. In approximately 600 million years, the moon will have moved far enough from Earth that total solar eclipses will no longer be possible. The moon will appear too small in the sky to completely cover the sun's disk, and the era of total solar eclipses will be over. Total solar eclipses are possible today because of a remarkable coincidence of scale and distance. The sun is approximately 400 times the diameter of the moon and approximately 400 times farther away, which means that both bodies appear almost exactly the same angular size in Earth's sky. When the moon passes directly between Earth and the sun, its disk fits almost perfectly over the sun's disk, producing the brief period of totality during which the corona becomes visible as a shimmering halo around the darkened disk. One of the most breathtaking sights available to anyone who has ever stood in the path of totality. This coincidence is temporary. As the moon continues to move away at 3.8 centimeters per year, its apparent size will decrease. In about 600 million years, the moon's apparent diameter will be too small to fully cover the sun's disk even during a direct alignment. After that point, there will be only annular eclipses, a ring of sunlight remaining visible around the moon's smaller disk. But the complete darkness of totality will be gone. Every total solar eclipse visible from Earth's surface today is, in the context of deep time, a rare and temporary gift, one that could not have existed without Theia. There is a particular kind of loss that is not like ordinary loss, a loss that is also simultaneously a presence, a continuation, a transformation so complete that what was lost has not disappeared but has been redistributed into everything around it, inseparably woven into the fabric of what followed. Theia no longer exists as a separate world. Its material is distributed between the moon, Earth's core, Earth's mantle, and possibly the deep structures of the lower mantle, making it simultaneously everywhere and nowhere in any single identifiable form. everywhere, because Theia's atoms are literally all around us, in the rocks beneath our feet, in the iron at the center of the earth, in the moon above our heads, in the tides that rise and fall on every coast. Nowhere, because the specific arrangement of those atoms that constituted Theia as an independent world, its structure, its interior, its geological history, its particular path through space, is gone, dissolved by the violence of the giant impact into a quantity of fragments so vast and so thoroughly mixed that no amount of future observation could ever separate them out and reconstitute the original world. Theia is the ultimate example of something that planetary scientists call accretion, the process by which small bodies become parts of larger ones, by which the material of one world is added to the material of another. But Theia's accretion into Earth was not slow and gentle. It was catastrophic and total and irreversible. And the resulting world, with its moon, its tilt, its tides, its magnetic field, its stable climate, its long history of life, is the proof that what was lost was not simply lost. It was transformed. It became something larger than itself. It became the conditions for everything else. The story of Theia is, when you trace it to its deepest implications, a story about the relationship between destruction and creation, about the way in which the most complete and final endings can also be the most productive and generative beginnings. The story of Theia is, in a sense, the story of how destruction gives rise to creation, a lost world whose ending made possible everything that followed, including the oceans, the seasons, and life itself. This is not a metaphor imported from outside the science and applied decoratively to make it more emotionally resonant. It is, in the most literal and verifiable sense, what the evidence describes. Theia ended. It ceased to be a world. Its structure was destroyed, its interior scattered, its identity as an independent body dissolved in a matter of hours. And from that destruction came the moon, a new world different from Theia, built from what remained of Theia's mantle and Earth's. From the moon came tidal forces that shaped the early ocean, drove the chemical concentration that may have led to the first living molecules, and stabilized the axial tilt that gave billions of years of relatively stable climate. From that stable climate came the time required for evolution to build complexity, from single cells to multicellular organisms, from simple animals to the extraordinary and still growing diversity of the modern biosphere. From that biosphere came, among millions of other things, a species capable of looking up at the moon and wondering, across all that distance and all that time, where it came from. Theia's destruction is not just part of the story. It is the beginning of the story. Every living thing on this planet is, in a very real sense, a consequence of what Theia gave when it ceased to exist. It is worth spending a moment with the counterfactual, with the question of what kind of world Earth might have been without the giant impact, without Theia, without the moon that Theia's collision created. Without the moon, and therefore without Theia, Earth's nights would be dramatically darker, its tides dramatically weaker, and its axial stability dramatically reduced, potentially changing the character of every aspect of life on this planet in ways too numerous and too interconnected to fully trace. A moonless Earth's nights would be lit only by starlight and the faint diffuse glow of the Milky Way. Beautiful, perhaps, but much darker than the nights we know and lacking the additional navigational beacon that the moon has provided to nocturnal animals for hundreds of millions of years. The rhythms of nocturnal life that have evolved in response to the lunar cycle, the spawning behaviors of corals and fish timed to the full moon, the hunting strategies of animals adapted to use moonlight or to avoid it, the navigational systems of migratory insects that use the moon as a directional compass, would simply not exist, replaced by different evolutionary strategies in response to a consistently darker night sky. The tides on a moonless Earth would still exist, driven by the sun's own weaker tidal force, but they would be less rhythmically varied and less environmentally dynamic. The intertidal zone that has proven so extraordinarily productive as a cradle of biological diversity and possibly of life's origin chemistry would be a narrower and less dramatic environment. And Earth's axial tilt, without the moon's stabilizing influence, might have wandered chaotically, producing a planet whose climate history was shaped by swings that no evolutionary lineage might have been able to track and survive intact. When planetary scientists and astrobiologists consider the conditions that might allow complex life to arise on a planet orbiting another star, when they try to identify the factors that made Earth habitable for the kind of life that eventually produced technology and civilization and the ability to ask questions about its own origin. One of the questions that repeatedly arises is how common the Moon's formation process might be in other planetary systems scattered across the Milky Way. Some astrobiologists argue that a giant impact like the one that created the Moon may be a rare event in planetary systems, making Earth's particular history and the Moon's existence unusual enough to have directly influenced the emergence of complex life here. The argument for rarity runs as follows. For a giant impact of the right size and angle to produce a moon of the right size, large enough to stabilize the host planet's axial tilt and drive significant tides, but not so large as to be catastrophically destructive to all subsequent habitability, requires a specific configuration of initial conditions that may not be commonly reproduced in other planetary systems throughout the galaxy. The impactor must be roughly the right size relative to the planet. The impact must occur at roughly the right time in the planet's development. The impact angle must be in the right range to produce a debris disk capable of forming a moon of appropriate size. Each of these constraints is plausible individually, but their simultaneous satisfaction may be statistically uncommon enough that Earth-like planets around other stars may frequently lack stabilizing large moons, and may have evolutionary histories significantly different from Earth's as a result. For all the progress that has been made in understanding the giant impact in the 50 years since the hypothesis was first proposed, the event remains, in important and genuinely humbling ways, still mysterious, characterized by uncertainties and open questions that ongoing research is slowly, patiently, and sometimes surprisingly working to resolve. The giant impact is one of the most studied events in planetary science, and yet 4.5 billion years later, scientists still debate its exact geometry, the precise size of Theia, and the details of how the Moon assembled from the debris. The exact angle of the impact remains uncertain to within a range of values. 45 degrees is the most commonly cited estimate, but different modeling approaches with different parameter choices produce different best fit angles, and the constraints from observations are not yet tight enough to definitively settle the question. The precise size and mass of Theia is constrained only indirectly, from the mass of the Moon, the angular momentum of the Earth-Moon system, and the isotopic chemistry of lunar samples. And different models interpret those constraints somewhat differently, producing estimates that range from Theia being smaller than Mars to somewhat larger. The question of whether the impact produced a traditional debris disk or a Synestia or some configuration between the two has not been definitively resolved. The question of how much of Theia's material ended up in the Moon versus remaining in the Earth has different answers in different models. The giant impact is the best constrained catastrophe in Earth's history, and it is still, in many of its most interesting details, beyond our certain knowledge. There is a kind of silent history carried in every object that has ever been touched on the Moon's surface, a history that reaches back not to the moment of the object's creation, or even to the moment of the Moon's creation, but further still to the formation and destruction of a world that no longer exists anywhere in the solar system. Every piece of the Moon that has ever been touched, by astronaut boots, by rovers, by sample collection tools of any kind, carries within it atoms that once belonged to Theia, a world that no longer exists as any kind of independent entity. The 382 kilograms of rock and soil brought back by Apollo astronauts contain, distributed among all their various minerals and glass beads and fine regolith particles, atoms of silicon and oxygen and magnesium and calcium and dozens of other elements that were once part of Theia's mantle, that existed inside another world for tens of millions of years before the giant impact blasted them into orbit, where they participated in the formation of the Moon, where they remained on the lunar surface for 4.5 billion years, slowly accumulating the cosmic radiation of deep space and the micrometeorite impacts of eons until a human being reached down with a gloved hand and picked them up. Those samples now sit in carefully controlled storage facilities on Earth, analyzed, catalogued, shared with researchers around the world. Humble pieces of rock that are simultaneously the most scientifically valuable geological specimens in human possession and the direct physical remnant of a vanished world. To hold a moon rock, in the imagination, if not in fact, is to hold a piece of Theia. The Moon's surface, in a very real and literal sense, is a record, a geological archive of the history of the inner solar system, preserved in the absence of the plate tectonics and weathering and biological activity that constantly erases and rewrites Earth's own geological record. The Moon's familiar face, the craters, the dark Maria, the bright highlands, is an ancient record, preserved in rock, of the violence and heat that followed Theia's end and the long, slow quieting of the inner solar system that came after it. The highlands, as we have seen, are the frozen surface of the original lunar magma ocean, the first solid rock of a world born from catastrophic collision. The Maria are the record of the volcanic activity that followed hundreds of millions of years later, as the Moon's interior partially remelted during the period of heavy bombardment and flooded the great impact basins with dark, iron-rich lava. The craters, the hundreds of thousands of craters visible at every scale across the lunar surface, are the record of that same heavy bombardment, the rain of impactors from the outer solar system that pelted all of the inner planets during the first billion years of solar system history. And beneath all of this, at every scale and at every level of chemical analysis, is the signature of the giant impact itself. The oxygen isotopes, the mineral compositions, the volatile depletions, all pointing back to the same event, the same collision, the same ancient moment when Theia ceased to be and the Moon began to be. The Moon's face is not random. It is a palimpsest, a surface written on many times with the oldest writing still legible beneath all the later layers. It is possible on a clear night when the Moon is full and high in the sky and the world is quiet, to look up and try to truly feel what you are seeing, not as a familiar presence, not as a decorative feature of the night sky, not as the reflected glow that lights a path or casts shadows in a garden, but as what it actually and literally is. A relic of an event that predates all life, all oceans, all continents, all chemistry that we would recognize as biological. When you look at a full moon on a clear night, you are looking at what remains of a collision that happened before any life existed on Earth, before oceans, before continents, before a single living cell had ever divided anywhere on this planet. The photons of sunlight that travel from the sun fall on the Moon's ancient surface and then travel 384,000 kilometers more to reach your eyes. Those photons are bouncing off rock that has been there in essentially its current form for longer than the oldest fossils preserved anywhere on Earth. The oldest evidence of life on Earth dates to approximately 3.5 to 4 billion years ago. The Moon's highland surface was formed 4.4 to 4.5 billion years ago. The Moon is older than life. It was old already when the first living cell divided in whatever warm and chemical-rich environment the first life found for itself. It has been watching, if we may speak of watching, every subsequent development in the history of life on this planet, from the first tentative chemistry to the first multicellular organisms to the first creatures to look up from the surface of the Earth and wonder at the light above them and give it a name. The physical Theia is gone, dissolved into the fabric of two worlds, its identity as an independent planet irreversibly lost in the chaos of the giant impact. No instrument will ever find it intact. No future mission will ever return a sample labeled clearly as belonging to Theia and Theia alone. It is gone in the way that only the most complete and final transformations are gone. Not absent from the universe, but present in it in a form so thoroughly redistributed that its original shape can never be recovered. But the influence of Theia, the gravitational echo of its existence and its ending, is woven so deeply into the structure of the world we inhabit that to live on Earth is, in a subtle and pervasive sense, to live in the world that Theia made possible. Theia itself is gone, but its gravitational echo persists in the tides, in the seasons, in the stable spin of a world hospitable to life, and in the quiet light that falls through windows on sleepless nights. The tides that rise and fall on every coastline of every ocean, rhythmic, patient, eternal by human standards, are Theia's legacy, operating through the Moon that Theia's collision brought into existence. The seasons that turn through the year, the lengthening of days in spring, the fullness of summer, the quiet withdrawal of autumn, the long silence of winter, are Theia's legacy too, written in the 23.5-degree tilt that the giant impact imposed on Earth's axis. The relatively stable climate that has given billions of years of evolutionary time for life to build its extraordinary complexity. That stability traces back to the Moon's gyroscopic influence on Earth's tilt, and therefore, at its deepest root, to Theia. The world is full of Theia. It always has been. Tonight, as it has done for 4.5 billion years, the moon will rise. It will rise over oceans that fill basins carved by plate tectonics that began after the giant impact. It will rise over continents built from rocks that were themselves assembled from the materials that the giant impact redistributed across the surface of the cooling Earth. It will rise over a world whose axial tilt, whose seasons, whose stable climate, whose tidal system, whose magnetic shield, all trace their origins, directly or indirectly, to the collision that created it. The moon rises tonight as it has risen for 4.5 billion years, a remnant, a reminder and a relic of a world that gave itself completely so that ours could be. This is not a poetic license. It is the most literal description available. Theia gave itself, every atom of its mantle, every trace of its chemical composition, every unit of angular momentum it carried in its final approach, to the making of the moon and the reshaping of the Earth. It did not do so willingly. It did not do so knowingly. It did so because that is what the physics of the early solar system required, and because the universe does not ask permission before it transforms one thing into another. But the result, the specific character of this specific planet, orbited by this specific moon, tilted at this specific angle, warmed by this specific sun, covered in these specific oceans, inhabited by these specific living things, all of it is the particular and unrepeatable consequence of what Theia was and what Theia became. The moon rises tonight, and with it, silently, in every tide and every season and every night that its light falls through a window onto a sleeping face, Theia rises too. And so, perhaps, we return. Return from the very edge of things, from the beginning of time as this world knows it, from the furnace and the silence and the slow, patient cooling of a planet finding itself in the wreckage of a collision 4.5 billion years old. Return from Theia, from a world that existed and mattered and gave everything it was, and come gently back to the room you are lying in, the weight of your body, the soft darkness around you, the sound of your own quiet breathing. Outside, if you were to look, the moon is there. It has always been there, or nearly so, moving through the same slow circuit it has traced since the first days of its existence, when it glowed with the heat of its own birth and loomed enormous in an unfamiliar sky. It is smaller now, cooler, quieter, and much farther away. But it is still here, still pulling the oceans, still holding the tilt that gives the world its seasons. Still, in its own gravitational way, keeping watch. Theia is everywhere and nowhere, in the iron at the center of the Earth, in the ancient rock of the highlands, in every tide that rises on every beach that has ever existed on this planet. It is in the angle of the seasons and the length of the day and the particular stability of a climate that gave life enough time to become everything that life on Earth has become. You did not know, perhaps, when you lay down tonight, that you were lying on a world made partly from a lost planet. But you were. You always were. Every night that you have slept, Theia was there, woven into the rock, into the iron, into the light falling through your window from a moon that would not exist without it. Let that be enough, for now. Let the enormity of it become, in the way that enormous things sometimes do when we hold them gently and without grasping, a kind of comfort. The universe is very old. It has been making something out of everything for a very long time. And you, here, in this room, on this ancient world, beneath this particular moon, you are part of what it made. Rest now. The moon will keep, Theia will keep, and morning will come in its own time as it always has, tilted and seasoned and tidal and alive.